Okay, good. Amin, what do you think? We good? Okay, welcome everybody. It's the last lecture. I know you're like sad to see the semester end, but you'll have a holiday to get over it. So, okay, so we're gonna try to talk about a bunch of different things today, which you can see listed there. And let's see. Okay, so course, let's see if there's, let me get rid of that chat. Okay. Course evaluations. Today's the last day, and I'll look in the break to see what the response rate is. I can't see what you said, but I can see how many people have sent it in. Make me happy, go click on it, say something. All right, profs hate to get like, okay, you got a 4% response rate. And you're like, okay, I don't think that's statistically valid. So I know it's better than that already because I checked a couple weeks ago, but go do it if you haven't done it. I'll post a link to one additional lecture that has some additional information like time domain multiplexed FPGAs. There's a company called Tabula that raised a lot of venture capital, a couple $100 million, made it interesting time domain multiplexed FPGA so it could change its configuration cycle by cycle, increased its logic capacity but gave it significant power issues. A bunch of the people from that company were hired from Altera, and one of the key things Tabula did is they put pulse latches in their routing drivers. That was part of their time domain multiplexing technique. So you can see that was actually pretty clever, and you can see how they used that kind of flowed into, I believe, Stratix 10. So soft errors, something we haven't talked about too much, is like radiation can flip SRAM cells. And this is an issue for FPGAs because you flip an SRAM cell and your AND gate turns into an OR gate. And until you do something, your whole chip is just doing the wrong thing. So what are some of the mitigation strategies for that? And novel programming elements. So one of those is Flash. In the last reading, if you want to do one more paper, there's a paper on Flash FPGAs. So SRAM-based FPGAs are the most typical type, but they're not the only type. Second most common is Flash-based, where you don't store the configuration in SRAM. You store it in a Flash transistor, right, where you have a floating gate. You can basically get the programming voltage onto the programming gate, and you can actually make that Flash transistor actually act as both your routing switch and your configuration memory, which is kind of cool. So if you like that idea, the last readings about it and the last lecture talks some about these different programming elements. So I won't know if you go and view it. You can view it if you like or not. You could save it till the middle of the holidays when you're bored, you're lonely, you feel the need for some reconfiguration. So that's my holiday gift to everyone, right? So you might be going, like, I was really hoping for a lecture on Flash-based FPGAs, and I got one. So is it all right? Yeah.
I've never heard of these time multiplex FPGAs. Is this a market flop, or did they do well?
It was okay. So Tabula was interesting from a business perspective. I had like a friend who was one of their senior engineers. It ran out of money, right? So I guess from the perspective of you raised $200 million and you spent it all and didn't turn a profit, it was an economic failure. They did make chips that worked. And for an interesting thing about Tabula is that's the name of the company, right, that did this. Their technology is interesting. It had this clever idea of put a pulse latch into every routing driver, and that acts as a register. That's very useful for time domain multiplexing. Also is useful for deep registering. So that's why Stratix 10, I think, took the same idea. Time domain multiplexing, the motivation for it is, this lookup table or RAM or whatever, for most of my clock cycle is not doing anything useful. Right? Like the data flows through this lookup table, and for the rest of the clock cycle, it's just sitting there waiting for more data, and that won't arrive till the next clock cycle. RAMs is maybe even more obvious. If I can clock my RAM really fast, I could actually time domain multiplex it. Okay, so they did both of those things. It required a big change to their architecture. It required their place and route tools to essentially think of it as a 3D architecture. So that was actually pretty interesting. They mapped the whole time domain multiplexed place and route problem to a 3D place and route problem. And the third dimension was time. And it actually works, right? It's actually like you look at it and it's a little bit brain busting, but it was kind of interesting. It all worked. So they did get better logic density. You could fit more in the chip. Throughput is a little hard to say. You can fit more stuff in the chip, but now you're time domain multiplexing. So did it get more throughput or not? It was hard to say. Power is a challenge, right? So we saw power is like 1 half CV squared F times alpha. This is how much do you switch? Okay, well, I've now taken all the configuration RAM that usually is not switching at all, and now every cycle, like multiple times per clock cycle, like I'm actually running a faster clock cycle and I'm cycling through a bunch of different configurations. That's a lot of extra power. So I think that was a fundamental technical challenge, that power, as they were doing this, became a bigger and bigger deal. And their architecture, I think, was fundamentally high power. There's another interesting economic thing. So they raised $200 million US, and they ran out of money actually quite a while ago, 10, 12 years ago. So in today's dollars, it's even more. But the friend of mine who was there basically said one of their challenges is like the FPGA industry is really hard to break into because you have to make a chip, you have to make a CAD system, and you have to make IP cores for like kind of all the major functions. And he says when you're a startup like this, even a pretty well-funded startup, you go into a potential customer trying to sell them on your new chip, and their spec for what you need to do in terms of IP is, well, I need all the IP that I'm using they're either with Altera or Xilinx. So I need all the IP I'm using there. The interface I want to use that's my Xilinx IP. You do what the Xilinx IP does. That's hard for a startup, right? So they expected they had to do the hardware. They expected they had to do the CAD system. They underrated how much they'd have to do on IP, particularly this quite challenging spec of just do whatever your competition did. So ultimately they're out of money. But they had a very interesting technology. And their founder is very interesting, Steve Teig. He's quite a technical visionary. I saw him speak while Tabula still had money at ICCAD, one of the big CAD companies. He's had multiple startups. His startup before Tabula, this time-domain multiplexed company, and he called their architecture space-time, which sounds very cool, so he was big on space-time. But his company before that was also really interesting. It was a drug company, so he has a background in CAD. So he's made, a CAD company, then he made a drug company, then he made a FPGA company. And the drug one sounds like it's out of place, right? But what he did is he was making CAD tools for drug design, okay? Like model how these compounds are going to interact based on their shape and so on. So it's clever. And his talk about that was interesting. So he built this complicated CAD tool to try to come up with drugs. He said when they started it, his goal was he was going to cure HIV. And they actually did find a drug that would interfere with HIV's replication. But the problem was that HIV could mutate very quickly. So it got around the drug. And the lesson he took from that is it has to be reconfigurable. You got to be able to make things fast. So I'm not actually kidding. This is like, so his next startup, he was like, time-domain multiplex FPGA, as reconfigurable as I could possibly make it. He actually had a happy ending of the HIV drug. They had competitors who also were coming up with HIV drugs, and HIV could also evolve around them. But if you put them all together in what they call a cocktail of drugs, the virus couldn't mutate around all of them at once. And that is now this treatment for HIV. So no one startup could actually solve it by itself, but when you put all their solutions together, it was, a case where putting them together worked well. The other thing he said, so there was a long-term happy ending for the HIV one, but he said, it was kind of depressing for a while. They spent all this time, and it turns out the virus mutated around it. So what actually happened instead, their big cash cow was, I believe it's Cialis, right? So it was, he goes, we set out to cure HIV, and we wound up making a competitor Viagra, right? He goes, it just wasn't as satisfying, right? You didn't have the sort of same sense of social good. So anyway, so that's a long digression on those topics. Okay, so that, for our background reading, so we'll talk some about these two papers today, along with a whole bunch of other things. I think you've got till the weekend to review these. So if you're kind of going, I'm short of papers to review. The first one I would say is easier to read, academic treatment of like why hard knocks on FPGAs are good. Second one, very good paper, covers many things in Versal. So it's basically like it's a very dense paper because there's a lot of interesting things in Versal, but also a very good paper to read. And we'll talk about some of them today. And then for next week, if you're going, well, I still want to read more papers, I got to do it. This is one on a flash FPGA. So as I said, it talks about the SRAM FPGA vendors don't like to talk about soft errors. Microchip, which makes flash-based FPGAs, loves to talk about soft errors. So you learn some about soft errors, and you learn about how you can make a flash FPGA that is basically very good if you want to shut the power down, and very good for flash, for soft error resistance. The reason it's very good for if you want to shut the power down is you can. You can shut the power down, it remembers this configuration. Okay, so when I posted the slides, you might have noticed, hey, I don't recognize any of these people. It's because it was a contest from last year. It was on purpose, right? So, so the actual, this year, people did very well. Okay, so this is my reference for, you know, like a high level of brilliance, okay? My reference solution, and through a certain amount of self-interest, I define that to be super good, okay? So I got 2.7 times 10 to the 8th. Yongkan Kao and Sohail both beat that by 2.05. Zhayang Ying did a little better still, 2.04. Alex a little better still, 2.03. Heran and Xioshen did very well, 2.01. And then by a whisker, Hongyan has first place at 2.003. So well done all. There's actually an unusual number of people to beat my reference solution, okay? But I've chosen to interpret that not that my reference solution is weak, but the class is extremely strong, okay? So yeah, nice job. I did not manage to get to the store to get Amazon cards, but the top first and second for sure. I'll send you out Amazon cards. I will see at what point my wife starts complaining about financial outlays to see how far down I can make it. But this is mostly about bragging rights anyway, so everybody who placed on this, those are very good solutions. It's actually a wide range of solutions too. So my iterative solution is a greedy algorithm that tries to pick what seems like the reasonable mapping for each RAM based on its configuration, and then followed by iterative improvement. Like look at what you're running out of and see, okay, I'm running out of this, can I convert an M8K to a LUT RAM because I got some of those left. So that's what my solution does. And it tries to do that iteration in an intelligent way. So Hale used simulated annealing, so iterative improvement with hill climbing. I can't remember what everybody did, but several of the next, I think both Alex and Ziyang used a mix of greedy solutions and iteration. And two of the top ones actually managed to map it into an integer linear programming problem. And obviously in slightly different ways because they didn't get the same answers. So they actually threw, I'm going to map this. Integer linear programming is like an exhaustive algorithm. If you make the constraints correctly and you don't run out of time, it'll find the solution. There are obviously multiple ways to do it because they didn't get the same answers. Okay, so now if there was only one formulation, you should get exactly the same answer from ILP. Clearly there's different ways to formulate it. So anyway, so it's also very interesting about a lot of high quality solutions that employed fairly different techniques. Okay, course concept map. Okay, as I said, one of my own grad students said he was confused. Maybe a concept map would help. I don't know, it's kind of busy, so maybe it doesn't help. But we're here. So basically following from the root, we're looking at detailed FPGA architecture. We finished looking at basic routing. Today we're gonna look at some stuff that's related to routing still. Clocking. So special kind of routing. We'll look at some that's coarse-grained reconfigurable arrays, which changes your routing structure, but also usually changes your logic blocks. How we can make systems that use more than one piece of silicon, because a lot of FPGAs do that, and there's some interesting technology there. And then we'll hopefully have enough time to get into another kind of interconnect, an embedded network on chip, and what that can do for you. So these things are all kind of related to routing, but all a little different. They're not like sort of the classic routing architecture. Okay, clocking architecture. So should we architect or fabricate special routing resources for clocks, or we just use the regular routing? We've got all this programmable routing. We can program it any way we want. So what do you think? Can we use the regular routing to make clocks? Alex, what do you think?
Probably not.
So you don't think we can do it? Isidore, what do you think?
Like you can do it, but like is it going to be performant enough? You know, particularly clocks are something you want to get fast, and you also have very high fan-outs depending on like every register.
Yeah. So Isidore's right. You can do it. I mean, you can make anything out of the regular routing. So we can make clocks out of it, but it's hard to make really good clocks. So why, you said basically a really high fan-out. Okay, so yeah, the fan-out's really high. Now you can make really high fan-out signals using the regular programmable routing. Why is it hard for me to make a good clock using the regular routing? So what makes it hard? Fan-out maybe is a bit of it, but I mean, I can do regular signals with fan-out. What do you think?
I know clock skew is an issue. You want to make sure you want to make the clocks run at their precise time in order to make it
Yeah, so if I use, this is often called a locally routed clock, and the basic problem is skew. So on all my data path, your regular signals, you're basically trying to make them fast. There'll be a few where you're actually trying to make it slow to solve a hold problem, but mostly you're just trying to make it fast. And in a clock, the main goal is not actually speed, okay? So if I've got 2 blocks here, and maybe my clock is coming in, let's say it comes in from an I/O, it's a low-speed clock. It comes in from an I/O, if this is a regular data signal, and I would probably come in, go on a wire here, go on a wire here. Maybe this is far away, so pretend there's a whole bunch of blocks in the middle, there's a wire here. I'll go past this one, go in, connect some more wires, go past this one, go in. And that's about the best I can do with this placement for a normal data path signal. For a clock, this is not very good. The reason it's not very good is the clock arrives much earlier at this pin than it arrives at that pin. And why does that matter? Well, if there's a register inside here, and I'm trying to send data out through a few lookup tables and back to this register, the fact that the clock arrived here late hurts me. My data launches late, and that comes right out of my clock cycle. Okay, so this clock skew directly hurts my setup time, hurts my clock period. And you could say, well, then I could take a different transfer. Let's say I got a register here, and it goes straight into this block. Okay, no LUTs in the middle at all. Okay, this one, the clock arrives early. If I actually route this with pretty fast wires, maybe it gets to this block at the same time or even earlier than this clock. Well, that's a hold time violation, right? I can't have this data, when you clock me with a certain edge, I can't in the same clock cycle, like the same clock edge, get my data to some dependent register. That's a hold violation, it breaks my design. So the clock skew hurts me in 2 ways, okay? If my clock skew, and often, as I told people, I ask questions like this on qualifying exams, and students will get messed up about, am I supposed to subtract or add the clock skew? If you just think about setup and hold, it's kind of easy, right? So with the case I've given you, the skew in this direction is going to hurt my setup. The skew in that direction is going to hurt my hold, okay? But there's no happy solution here. Like it's, whether I make this clock early or this clock early, the skew is going to hurt either my setup or hold, okay? And if I take this, and this is a fan out 10,000 net, and I do this all over the place, I've got all sorts of different clock skews, and it's going to make life hard for my CAD tool. I'm going to have trouble fixing this up. Does that make sense? Now, what I could do, and CAD tools actually, many commercial FPGA CAD tools do actually, just in case you run out of clocks, they will have a low skew routing algorithm. So what a low skew routing algorithm would do is it would say, okay, don't do this. A special routing algorithm that says, come out on a wire here, go along on this wire, go along on this wire, go along on this wire, go in, and from this wire, go backwards and go in. Okay, so I've taken a longer path to get here than I needed to try to balance the skew. It's better, okay, but it's still not fantastic. It's not fantastic because the routing patterns here weren't really optimized to do things like make U-turns. And if I had to do one, it's probably not too bad, but if I have a fan out 100,000 nets and I need sort of U-turns all over the place, I might have trouble getting the exact amount of wire I want. I might be off by 1 or 2, so I still get some skew. These wires are somewhat granular in delay. You know, they have 200 picoseconds or so of delay. So doing this will improve my skew quite a bit, but it's not going to get rid of all of it because my routing patterns weren't really designed for this and the routing's a bit granular. Yeah?
Solution at the input to each lab, you put a programmable delay, and then basically you just do the routing as you normally would. You calculate what the difference is between everything, and you just readjust what the delay is so they get there.
Okay, so that's a good solution. So you're saying, hey, let's put delay chains in here, right? And a delay chain is a common FPGA element. So to show you what it looks like, it's pretty relatively small. It's a chain of inverters. You build as many inverters as you think you need for the delay, and then you basically put all those into a mux. Okay? Actually, let's say these are pairs of inverters. That way I don't have to worry about some are positive or negative. So these are all pairs of inverters, and this goes into a mux, and I have some SRAM cells that are controlled by the CAD tool, and the output of that is I can optionally delay my input, right? I could take it with little delay or a lot of delay. And you're right, I could use that to equalize out these delays, so that would help. But let me tell you the next problem. Are there any other issues with this? So we talked about not really good for low skew patterns. I have to make a low skew clock running algorithm, makes it better, but still not great. What else? Yeah.
Congestion.
Yeah, I might chew up a lot of this wiring, but my alternative is going to be to make a dedicated network. So, I could also just build more of this routing, so maybe that's okay. Anything else? There's some other fundamental things that I cannot fix here. So Isodor's clever, right? He said, like, let's put this delay chain in, and that does actually fix some of my, I can use that to fix up some of my skews, so it's a good solution. But is there anything else that's going to go wrong for me? So skew is basically the delay that you know is going to happen every single clock cycle. Like there's just a difference in clock delay between here and there. Yeah.
Jitter.
Yeah, so you can also get jitter. That's where your edges move back and forth. That's actually even worse because here I showed you my skew will kind of hurt my setup or hurt my hold depending on which direction it is. Jitter hurts it both ways because it says this edge moves back and forth. Sometimes it's early, sometimes it's late. When you timing analyze, you got to do both. Okay, why is the jitter worse? Because these wires are beside each other. This wire and this wire, let me put another wire in. So say there's another wire here that's just doing something else, right? Some signal's coming from halfway across the chip. This signal is capacitively coupled to the wires beside it, okay? What that means is when the signal on this wire rises, it effectively injects charge onto the two wires beside it through capacitive coupling. That makes, if you're doing a rising transition on those, they actually transition faster. It helps them. If you're doing a falling transition, it hurts them. It transitions slower. And on different cycles, this wire might not be changing. It might be changing low to high. It might be changing high to low. So basically what happens is this capacitive crosstalk means that you have to assume a spread of your clock delays. And that spread is the jitter you have to assume, and it directly hurts both setup and hold. You don't like it. Okay? Yeah?
Okay, cheeky answer. CAD tool places known values that are constants along the line.
Okay, so you're going to have the... I've actually written code to do that, okay, in a commercial setting. So, and we wrote it in an afternoon. We wrote it in a hurry. So it was not on purpose, okay? Yeah, so you actually can do that. You can say, well, tell me, the CAD tool, we're going to basically tell the CAD tools which wires are next to each other. And the CAD tool could say, don't route a signal on this wire. If we don't route a signal on it, we'll program it to just be connected to ground. And it basically doesn't transition. There's no capacitive coupling. It actually shields you from the wires around you. You won't get much coupling to this wire because this acts as a shield. So you can do that. It's a very expensive solution because you wind up, like if I want to protect this wire, I need to ground the two wires on each side of it. Your routing patterns are such that you've staggered these wires, so you wind up grounding wires all over the place, okay? So it's a very expensive solution, but it can be done. Why did I write this code? I wrote this code at least twice. It was in two different chips because it was a mistake in the chip. I told you, the crosstalk I just told you about is what's called the capacitive coupling that changes your delay. If you get enough capacitive coupling, and let's say I have a wire here, and I have a wire on each side of it, and both these wires go from low to high at the same time. And there's enough capacitance between them that a buffer hanging off of here, okay, so there's like a buffer that's maybe going to go onto the next routing driver, maybe it's a pass transistor and then a buffer, that basically this actually, if this signal is being held down by another driver, so it's supposed to be a 0, but I actually inject enough charge that temporarily this reads it as a 1, it actually starts sending data down to the next wire. Eventually, this pulse where this went high will go low again, and this will go back down to 0. But what I just did is coupled timing paths, okay? Like this might have been right near the end of my clock period. Just before these two wires settled down, got the data to the register that's capturing them, they triggered a pulse on this. And the pulse was big enough to make it through the downstream routing driver, which means it can now propagate maybe through all the wires until it gets to its final register. This just breaks static timing analysis. Like all the timing paths in your circuit just got coupled. So this is unacceptable. If this happens, once it's discovered, and it's discovered through great pain, your CAD engineers get a very bizarre request of make sure you don't simultaneously use these wires and these wires and these wires. And then we had to put code in the router to basically, okay, when you do this, you got to get shield wires and so on. So yeah, so you can do things like that. For clocks, you can write shielding code, but it's a mess, and it's inefficient. So for these reasons, we actually want to have a dedicated routing network for clocks. You could route low speed, low quality clocks on the general routing, but they're not going to be that good for high speed. Does that make sense? Okay. So I already said all this. So we need to build a low skew routing algorithm. Still not going to be, we're not going to get really low skew clocks. Crosstalk's going to add jitter. Oh, another one thing, something I didn't mention. If you actually look at the Cordis timing report, you'll also see that it has like another piece of jitter basically, or skew that comes from on-die variation. So on-die variation is I made these two wires. Well, I'll say this wire and this wire. I laid them out to be, they're very similar. They each have a certain delay. But in reality, when you're manufactured, both the wires and the driver driving them is going to have some variation from the other ones. And that has to be modeled. And on a clock, that variation, again, directly hurts you. It behaves just like jitter. It's like the signal might be a little early, it might be a little late. The CAD tool has to worst case it. It comes right out of your setup and right out of your hold. How do we minimize on-chip variation? Basic technique is to make things bigger. Okay? If you make this wire fatter, put it high in the metal stack, and you make this buffer larger, it's got bigger transistors, you'll have less variation because just statistics work for you more. You have really small transistors, a very small change in how they are etched, like, well, the dopants that go into them or the exact gate length has a large percentage effect. You make everything bigger, it's not so bad. You don't want to make everything on your chip bigger, but for clocks, you will actually often make it bigger than you needed to in order to try to minimize variation. Variation is not as bad on your regular data path, right? You just, for setup, you just always take the slowest. Okay, so slowest hurts you, but something being faster doesn't hurt you. On a clock, being faster hurts you just as much as being slower. Okay, so variation is fundamentally worse on clocks. Does that all make sense? Okay, so all of this means we would like to have some special programmable networks for clocks. Let me see if there's, okay, that's just a mean. Okay, so we want special programmable networks for clocks. So what should we build? So I've convinced you, you probably want a special clock network, or maybe you like the challenge, you're like, no, I'm just gonna write all the CAD out, it's just gonna be fine, right? So you could do that. What do you think? Yeah, you're gonna build a big tree, and the classic clock network has a special name. So does anybody know what it is? Yeah, so it's an H tree. So this is the classic clock network that gets used in ASICs, for example, or it's the most common one you would use in ASIC. It's called an H tree because it looks like a bunch of H's, right? So here's one H, then it's basically a fractal pattern. It repeats, right? This is another H, and so on. Okay, now why would you route something like that? Well, this is my drive point to the clock. And in FPGA, you always want programmability. So what have I done? I put a routing driver here. I got a mux, and I got a buffer, typically a pretty big buffer, right? So it's not one inverter, it's probably a cascade of like at least two, but maybe even four, so the last one's pretty big. Okay, and that drives a big piece of metal, and then I go through another buffer, probably pretty big, because I want this to have minimal variation, and it drives another piece of metal, and so on. And eventually, at the ends of this, I will actually connect to registers. Okay, so what's useful about this? If I have a register here, which is pretty close to my drive point, like that's not very far away from where I'm driving the clock, the path to get there is like this. If I have a register here, which is pretty far away from my drive point, the path to get there is basically the same length, right? So while it's possible to reach this close register with considerably less metal, I on purpose don't want to do that, right? I make it go further away and come back. So this pattern means that no matter where I am on the chip, I'm going to go through the same amount of metal, or very close, and the same number of buffers. So it's skew balanced. Same delay everywhere, whether I'm far or close. Does that make sense? Okay, I also, I said that crosstalk's an issue. Well, I shield these. Okay, so it's not shown in this diagram, but basically beside these wires, I'm going to have some grounded or VCC wires. Doesn't matter. As long as they don't switch, that's fine. They're shielding. I can put these high up in the metal stack, use pretty thick, wide metal, and pretty big buffers. That minimizes my variation. So I've now got a much higher quality clock. Putting them high up in the metal stack is also helpful because that's where you'd like to run most of your power and ground. So you need to put power and ground somewhere where you don't have much resistance. That's up in your metal stack, so you kind of got shielding wires anyway. So you put your power and ground all around your clocks. Okay, so one thing I could do is, okay, so FPGA designs don't just have one clock. So in an ASIC, if I know I've got one clock, I could build one H tree. If I know I've got two clocks, I could build two H trees. In an FPGA, we're building one chip, and everybody's got to use it. So, and I generally am not going to have more than one clock. So what I could do is I could say, well, 4 clocks is enough for everybody. I build 4 H trees. I build one of these muxes in front of each one of them so that you can choose a different signal to go on each, and that's it. So what do you think? I guess if 4 clocks was enough, that's pretty reasonable. I guess so maybe this boils down to, is 4 clocks enough? Yeah?
I don't like it because the other thing that you notice is that likely different clock domain logic is going to be geographically together on your chip.
Yeah.
So you'd rather this clock network be programmable in some way so that you can basically break your chip into sectors or something, and each one is driven by a different clock or has the option of being stitched together.
Yeah, so I agree with Isidore. Isidore is saying, yeah, so maybe people online, hopefully you can hear that. If not, you can type in the chat. So go ahead, Alex.
So to answer your question of whether the mux is actually bad, a lot of circuit designs can actually have upwards of like hundreds of clocks per design, so you need a lot more than 4.
Yeah, so just building 4 clocks, not great. And Isidore's also pointed out having, so I could build like 100 then. I could say, well, forget 4, I'll have 100. But it seems kind of wasteful because I probably don't have 100 clocks that all go all over the place. So I built 100 clocks that each cover the whole chip. It's kind of wasteful. So, whoops. Okay, yeah, so we can have more than 100 clocks in an FPGA design. They don't all have that. I had a summer student, he's a great summer student actually, he wrote a journal paper with me. But I spent the first 2 weeks of his summer term trying to convince him that you sometimes need more than one clock. Because in his 241 course, they said don't use more than one clock, which is a good idea. Sometimes like students when they're first doing digital logic, they want to do logic on the clock as well as the data. But he'd absorbed that lesson and just decided one clock's always enough. So why do I need more than one clock? Well, I need a lot near IOs, right? PCIe, DDR, SONET is an optical communication standard, but you send data in electrically. Those all have very fixed frequencies, so you got to produce clocks for those frequencies. Some of them, like let's take DDR. Okay, so DDR, I said, is a source synchronous interface. You send strobes alongside the data. So there's one going with the outgoing data, there's a different one coming with the incoming data. And then it's actually double data rate. You actually have to drop the clock down from double data rate to single data rate by widening the bus. You drop it down some more because the FPGA can't keep up. Turns out the data and the command buses are on different clocks. So for a single DDR interface, you need, well, in Altera's IP, depending on the exact type, it was 5 to 7 clocks. That's for one, okay? Typical FPGA could have 6 of those. And they all use different clocks, right? Because the idea is that it's source synchronous. The clocks are kind of similar, but they're not actually exactly the same. So, yeah.
Sounds like these designers need to take 241 again.
I was going to say, they're using 5 to 7 clocks and doing well.
You could do that if you wanted to communicate with your memory at like 60 megahertz. That'd be totally fine. But if you go out with your 60 megahertz, DDR 0.11, you're probably not going to sell too many. So that's the downside. Okay, so we do get a few big ones. So we get a lot of little clocks near the IOs. These don't tend to go all over the place, but there's a lot doing specialized stuff. Then we do tend to get maybe one system clock, but often a few major ones. Why a few major ones? Well, because this thing is talking to PCIe, and it's natural for it to use the final clock that comes out of PCIe. This thing's talking to DDR, et cetera. This thing's doing Ethernet processing. So I can wind up with more than one system clock that's pretty big. So we could pre-build 100 H trees, but you guys already told me that doesn't sound very good. Okay, that sounds wasteful. And it is. So the part that's most wasteful is the bottom of the tree. When you get down to the end of the tree, in every channel that's going by your logic blocks, you'd have 100 of these clock wires. Like the top part of the tree is not that big a deal, right? If I go back here, you see like, this wire is like one wire, okay? But if I go this far down, I've got 4 wires that intersect. And if I kept repeating this pattern, when I get to the bottom of this tree, if I have like 100 well, 200 rows in my chip, I'll actually have 200 of these little pieces of metal. So where I spend most of my metal is actually low in the tree. But down there, this is a lot. If I have 100 wires in every channel that are getting my clocks past every little logic block, well, a commercial FPGA is typically like 200 to 300, depending on how the logic block and routing is designed, 200 to now sometimes 400 wires in a channel. So 100 is actually a lot. And especially if I'm going to make these extra thick and shield them, they're even more expensive than they appear to be. So that doesn't sound great. OK, so I think Isidore already gave one idea. Well, but you give an idea of like some of these clocks are not very big. So I guess that's not a solution. That's a problem. What do you want to do? Yeah.
So one idea is that you take that center wire and you make, however many 200 of them that you need. And then at the edges of the center wire, let's say instead of having 100 of the second level of the tree, you'd have fewer and you'd have muxes that you use to decide which of those bigger wires get passed down the tree.
OK, so that's a good idea. I'm going to stop you there. OK? So you may have more ideas, but we're going to go with that one. So, so this is actually kind of a variation on what Isidore just said. Well, maybe it's not exactly the same, but we're going to get to what you just said too. So one is you can build some big and some small networks because you're not going to have 100 clocks that all go everywhere. It doesn't really make sense. Every register in the end gets one clock. So a lot of FPGAs have used this technique. So many generations of Altera chips, for example, use this. Build some number. So we use 16 global clocks. So we did build 16 H trees. But then essentially we built 64 quadrant clocks. And a quadrant clock covered a quarter of the die. Basically, a quadrant clock looks like 1/4 of an H tree. You basically just delete the top part of the H tree, and what's left is actually 4 little H trees. So if I actually needed a bunch of little H trees, I just got them by deleting something. So that seems pretty good. So the cost of these red things, of which I have 64, is the same, or in fact slightly less, than the cost of 16 global clocks. And I could make even smaller ones if I wanted, but this is pretty commonly done. We would make full chip clocks and quadrant clocks. We can also use Isidore's technique. So Isidore's technique is, well, the top part of these H trees is not that expensive. The part that is expensive is when I get down towards the leaves, because that's where I got lots and lots of branches. And that means lots and lots of wires, lots and lots of drivers. And what I can do down there is essentially use the fact that in any local region of the chip, I may not know which clocks I need, but I know I probably don't need that many, right? I just don't know which ones. So, and this is also done in both AMD and Intel FPGAs. So let's say that after my previous trick, in every quadrant of the chip now I have 32 potential clocks, right? 16 that go across the whole chip and 16 that are for my quadrant. But that even 32 wires starts getting expensive when I get down near the bottom of these trees. It's better than 100, but it's still expensive. So as I get down to the bottom of the trees, well, this is what Altera does. They don't build all 32 of those networks. They build the last little bit. They stop building an H tree, okay, because you can just make the last. You can stop once the arms of the H are getting really small. You can just say, I'll make a last wire that goes past some number of blocks, and the delay of that wire is small enough that there's very little skew. Now, it's a little bit, but I'll save the area, just make one wire. As long as it's relatively low resistance, so it's on high metal and it's not too long, the skew's small. So you do that, and then what we've done here is we haven't built 32 of them, we just built 6, okay? But we put a mux in front of them. So all 32 of these clocks compete for these 6 final stage, Altera calls them row clocks, okay? And the CAD tool basically has to count during placement in this region. And in a lot of the chips I worked on, that region was like 1/8 of a row. As the chips have gotten bigger, it will be less than that. So maybe, maybe it's 1/20th, maybe it's 1/40th of a row. So it might be 10 logic blocks, it might be 15 logic blocks, but it's not an enormous number. The placement engine basically keeps track of how many clocks am I using there, and it forbids any placement that uses more than 6. And that guarantees that this will be feasible. When placement is done, we're going to basically program these muxes to choose those 6 clocks to go out here. Now, and we actually did experiments on this. If we made this 2, that hurts the placement engine quite a bit, okay? It's now starting to perturb the placement a lot. But at 6, it didn't have to perturb the placement much. We couldn't really record any degradation. We actually, in StratX, we did 8 because we were conservative. StratX 2, we dropped it to 6 because we couldn't figure out why we did 8. Like, we were just worried. We couldn't really measure any difference. And then we stayed at 6. Like, all the chips after that I worked on stayed at 6 because if we went below that, we started being able to tell, okay, it does hurt some designs. And the savings was pretty substantial to go from 32 wires down to 6. You know, push us down to 4 and 3, you get some savings, but you don't want to do it if it starts causing, you know, degradation in other metrics. So yeah, Altera did this. AMD also does this. Okay, so they sometimes if you look at their diagrams, AMD and Intel draw their chips rotated 90 degrees. Okay, so I'm not going to show exactly what Intel does, except maybe I have a picture from a paper. Just rotate this whole image by 90 degrees, which makes it confusing, but they have the same idea. Okay, so yeah.
One other question is, can you take it even further, where you have like where each of the buffers are that you see there, the triangles, replace them with muxes, and then basically just have like many, many levels of hierarchy. So like in the center, maybe you have 100.
Yeah.
And then the next level is maybe 50, and then 25, and then just keep making it smaller as you go down the hierarchy. Where you start with basically you can route any clock from the center, no matter which path you take, you're going to go through the same number of muxes, so the delay isn't bad.
Yeah, that's a good idea. You could do that. So, and in fact, that kind of leads to the next technique. So basically, all large FPGAs that I know use these first two techniques, except the first one. Okay, so what are those two techniques? Mux at the bottom, okay, and have the placement engine count it, and then kind of make a diversity of top-level networks, right? Some bigger and some smaller. So the latest chips from AMD and Intel went one step further, kind of in line with some of the things that Isidore was just saying. And what they did is they don't prefabricate the top level. Okay, so in these architectures, basically there's no programmability in these buffers. Okay, they just, normally you can turn them off. You can turn them off to save power if nobody's using that clock. But other than that, there's no programmability. So these black lines are 16 full chip H trees. The red lines are 64 quarter chip H trees, and that's all they can be. So starting with StratX 10, what Intel did is they basically said, let's make essentially a more flexible routing network for even that top level of the routing tree. So they made 32, essentially like a channel, but there's only a few of these channels. They don't have to be in every row. They're just in certain spots. And they put 32 wires in them. They're shielded. They have big drivers to minimize variation. So all these wires are good for clocks. And they put actual switch blocks in. Okay, so there's programmable interconnect switches. So you can basically take these prefabricated, very friendly for clocks wires and can turn them into anything you want, right? So the CAD tool actually builds what it needs. So what can it do? So it can build a full chip H tree. Okay, so it could combine them, and it has an algorithm in it that knows how to make H trees. So if you need a clock that goes everywhere, it makes you an H tree out of basically one of these wires from each bundle of 32. It can combine them in that way and make an H tree. But if you need maybe some weird stuff, I need a clock that goes here and here, it can actually make you that without making the whole H tree. It just makes the pieces it needs. Why is that useful? Because it could fit in the pieces it needs for another clock, also skew balanced, H tree-like, but not building the whole H tree, again, out of these 32 wires. That's used on kind of a coarse granularity called a clock sector. Once you get into a clock sector, so this, what I've just circled, that size, you go back to that spine and rib clock. Spine and rib clock is the muxing structure that I talked about. You have some wires going this way, and you mux out of them to go the other way. So it still uses that trick of doing muxing and having these ribs that go past a certain number of logic blocks at the end. But the top, instead of being prefabricated, H trees of various sizes, they just make you a pool of wires that are good for making the top part of clocks, and you make it yourself with a CAD algorithm. So Intel did this, and in Versal, the latest Xilinx generation, they also do this. So that follows the, once both big vendors do it, you can probably be pretty sure that that's what they're going to keep doing. Yeah.
I was just curious. So this is probably generated. The clock is probably generated using PLLs, and from here it looks like the PLLs are like on the edge of the chip. And in the previous
The PLLs are normally on the edge of the chip. They don't have to fundamentally be there, but you usually put them near the IOs, and they also like there's some analog components in there which they like a clean power supply. So you try to actually give them their own power solder balls and so on. But you can route a wire from them right to the middle of the chip, okay? And you shield that wire. On clocks, you actually don't care so much about delay, you care about skew, okay? So you try to keep your delay from getting hugely big because you're on die variation, like say your transistors are 2% faster. Well, 2% of your delay. So that means that uncertainty grows if your delay grows. But that's basically where you care about delay. It's like a second order effect. The first order thing you care about with clocks is what is the difference in delay, not what is the delay. So going from the edge to the middle with one wire is not a huge deal. And normally, yeah, so on these architectures that I'm showing you here, like what goes into these muxes can come from a whole bunch of different spots, like 2 PLLs, 1 signal from the general routing, 1 signal straight from an IO. Some of those might not be near that spot, so they had like long shielded wires to get there.
So it doesn't necessarily have to be a PLL.
No, in fact, normally you can drive a clock network from anything. A common use is you drive it from a PLL, because if you're trying to make a fast clock that is high quality, you usually use a PLL. But you can get them from the general routing. You can get them directly from IOs. You can get them from your serial transceivers, because your serial transceivers will make a clock out of the incoming data. Some of the earlier Altera chips I worked on, actually, like you couldn't get there from general routing. That's a bad idea, because it turns out that if you think no one will ever do this, you're wrong. Somebody's doing it, usually at Nortel. So at Nortel, they're all doing it. so it's actually much safer to say you can get there from everywhere, even if the most common use is from a PLL. Like once you can get there from the general routing, that actually means anything can get there. So yeah.
So following on that, can you use your clock network for signals that aren't even clocks, like for instance an enable?
Yeah, you can. They're usually not used for anything other than clears. So if you have an asynchronous clear, its behavior is similar to a clock of you care less about its delay and more about its skew. You want everybody to come out of reset at the same time. You can use it for other signals, like some big enable. Because clock networks are optimized not for delay, but for skew, it's not usually beneficial to put even a really high fan-out network signal on it. Usually going through the general routing is actually going to be faster. It's just going to have more skew. But you can do it. It's legal.
Also like routing stress though, because if you put it through general routing, you may be consuming wires everywhere.
You could do that. If you're really running out of wires, you could run it through a clock network. That's true. But because the clock network tends to use bigger drivers, thicker metal, it's kind of a high power solution, and it gets you a low skew, which you didn't care about. You really cared about high speed. So it, doesn't. You can do it. It's usually not done that much. So. Okay, so anyway, so this is, and I know this algorithm is actually tricky, because I know that for a while the clock skew was worse in Stratix 10 than the previous generation for quite a while. But it has improved, and it looks like this has become the new dominant way that everybody's going to do it. Okay, so I told you Xilinx has followed a relatively similar path. Yeah, this is rotated 90 degrees. So this is basically the top of the clock tree, and in all Intel chips, this would be horizontal, right? That's that last level after you muxed it. Maybe next year I'll like rotate the slide by 90 degrees instead of asking all of you to rotate your head by 90 degrees, but didn't occur to me till now, okay? What Xilinx did, which is quite clever, is they went, okay, I've already got this muxing in here. What I'm going to put in is I'm going to put a little bit of gating in, okay? So I put an AND gate in that I can configure. That's clock gating. Okay, so what's clock gating useful for? Power reduction. Okay, so I can always just send the clock to everywhere, and any register that doesn't need it just ignores it. We just configure them to not pay any attention, but that does chew up some power. And clocking usually takes on the order of 10% of your dynamic power, so it can be significant. So by putting these enable gates in there, Xilinx made it possible for designers who care about power to put a signal in to say shut down this branch of the clock when the signal's not high, and you could save some power. The other thing they did, which is even, I think, more useful, is they put a delay chain in. Okay, so delay chain, again, looks like this. Just a bunch of buffers with a mux that you can configure how far through the set of buffers you go before you take the signal out. And you can see kind of why they did that. It's actually called the time borrowing circuit. So why do you think they did this, given that name? And you can't just say time borrowing. You have to find like at least a synonym, okay? So this is not a literacy tests are over at the end of undergrad, okay? So, yeah.
So to take for oneself, help oneself to use as one's own, abscond, carry off, time.
Okay, yeah, so I'm gonna show you what it's useful for. Okay, so this is just a picture of what it looks like. So I guess I already showed you this, right? You've just got a bunch of buffers and a mux that you can program SRAM cells to say how long do I want to go. They did another clever thing. If they can actually take the end of this delay chain and connect it into the start of the next clock's delay chain, which basically allows them to make longer delays. If they didn't need the actual next clock wire, they can effectively go through 2 of these delay chains in series to make a bigger delay without adding more area, right? Because these aren't super expensive, but it does cost you more area the more of these inverters you put in series or buffers you put in series. So that was clever. Okay, so what do? Basically, the CAD tool decides I'd like to have a clock that's a little bit delayed available to these logic blocks. Why do I want that? Well, because I think I've got a difficult timing transfer. And if you actually delay the capture register clock, you give me a little bit more time. And that I've decided that is useful. That's called time borrowing. Okay, it's time borrowing because I get more time on one cycle, but I have to give it back, right? Like that register now launches its data late, so I better have some slack on its output. It's cheap. The reason it's cheap is because there are a reasonable number of these delay chains, but much less than if I put them in every single logic block. Because each of these last stage of clocking wires, like these rib clocks or leaf clocks, they fan out to maybe 20 or 30 logic blocks. So this is not a bad place to put delay chains. I don't have to build so many of them. Okay, so here's an example of how that works. Okay, so I've got this clock coming past. This is from the clock distribution network. So the upper parts of the H tree, or that structure I showed you. And I'm actually gonna take 2 versions of this clock. So I've got, say, 6 of these. Actually, maybe I have it on the previous slide. How many of these do they have? Okay, so they actually have 16 of these like leaf clocks. Okay, so they mux down their upper clock distribution with 16 of these things. And it turns out that in this group of, 32 or so logic blocks that this fans out to, I don't need 16 different clocks. So they're going to take this clock twice, once through here and once through here. They're going to put on 2 different leaf clocks, that last wire. And in the green one, they're basically turning on the extra delay chain. So these 2 clocks are logically the same, but this one is later than this one. They've intentionally delayed it. So let's say inside this logic block, see if I can draw this well, I've got a register, and then it goes through a lookup table, and maybe another lookup table, and then it goes into this register. And let's say that path, I'm running fast enough that path is actually timing critical. I'm having trouble getting it done in 1 clock cycle. Then delaying this second clock helps me, right? I give a little more setup time. Now it does hurt me on whatever this feeds. Okay, whatever this feeds, I launched my data a bit later, so I better have a bit of timing slack there, but often that is the case. The other thing that I have to watch for is, let's say there was another register in here, and let's say it went straight into this LUT. Okay, so this second path that I just drew in this somewhat messy diagram is quite a bit faster. I have to make sure that path is not so fast that I can get from this new register to this register, in the same clock period. Like that puts a constraint on how much I can slow down that clock. But I can probably slow it down by some, right? Like this can't be infinitely fast. There's at least 1 routing wire between these things. So they use this technique to gain some extra speed, particularly on high-speed clocks. Like where this is useful is where you have a clock that's running pretty fast, so the clock period is pretty short. So even getting an extra 200 picoseconds on a 2 nanosecond clock, well, that's 10%, right? So it's most helpful on really fast clocks. Yeah?
So with that other wire, the whole time violation, you just route that wire to just a longer path through the routing until it happens.
Yeah, that's true too. So let's say that you have some iteration that you can do in the CAD tools. So a logical way to do this is you wait till the design's totally done. You've placed it, you've routed it, you know everything, and then you skew the clocks. But let's say you do that and it turns out you're going to get a hold violation. Like you'd like to slow this red clock down even more, but you can't because it's going to cause a hold violation. Then what you could do is for that path that is a hold violation, reroute it and say your goal, you used one routing wire before, your goal is to use at least two. And now you can fix it. So you're right. So you can iterate. It can give you some more margin for time borrowing. Okay. So these are the results from that paper. It's a paper on ultrascale, the architecture before Versal. And Xilinx also made their registers capable of being pulse latches. So they didn't actually make them that you had to be pulse latches. They basically made them configurable so you could skip the second latch so they could be pulse latches. So in Stratix 10, Altera, the registers that are in the interconnect, they said must be pulse latches. Xilinx said we'll make ours still in the logic block and they can be pulse latches. It doesn't save them any area, but it gave them the ability to turn them into pulse latches. And remember, pulse latches have another form of time borrowing where if you widen the pulse, you get something very similar to this kind of time borrowing. What they're showing here is what speed gain they get. And the green line is what do they get with clock skew scheduling. Clock skew scheduling is using the delay chains I just showed you. And it depends on basically how much hold margin, like you're often not quite sure how much hold margin your registers need until the chip comes back, you do a lot of characterization. So this is basically how close to the clock edge can they change things. If they actually have quite a bit of hold margin, then they can get about 7% speed improvement. And they'll actually get larger numbers on the fastest clocks, which are the ones you usually care the most about. If it turns out their registers, they can't push it that close to the edge, they get somewhat less because they have to be more conservative. So but they still get about 5%. The pulse latch, they basically show it also gets gains, but it's more sensitive to hold margin. Like they get bigger gains only if if hold is pretty good. Like the low level hold, basic hold time of the pulse latch is pretty good. And then they show they do stack. So the blue line is what if you do both techniques? So you get some additional benefit, but they find clock skew scheduling was more powerful. Whoops, that's weird. Okay, and yeah, this is what Isidore said. So these are if we don't have the router reroute anything. You could get larger gains still if you say, we'll create some problems, but we'll then re-invoke the router to fix up the hold times. We could get more gains still. Okay, so you can get a reasonable amount out of clock skew scheduling. It's similar to retiming, right? Because you could say, well, why do that? Couldn't I just move logic across the registers and I never need to move my clocks? Because they are essentially mirror images of each other. It's true, but clock skew scheduling is basically more fine-grained. You can essentially move things around by 20 or 30 picoseconds, whereas moving a lookup table on one side or the other of a register is a relatively big change. Does that make sense? So it's still useful even when you have retiming. Yeah?
So then doesn't all of this stuff kind of mitigate the case for things like hyperflex, where you have all this flexibility to play around with the clock and move your register effectively?
Well, so that's what AMD has chosen to do, right? They basically, in Versal, they went further with clock skew scheduling. They stuck registers in the input as well as the output, and they put delay chains in the logic block as well as on the clock spines. So yeah, they basically said what we need is a fair number of registers and then clock skew scheduling. And Intel has said, no, we want huge numbers of registers. As I said, the Intel architecture allows deeper pipelining. One of my graduate students did a study of how, in Stratix 10, how many pipeline registers do you need to go across one of the big chips if you are clocking it at the maximum frequency the chip can handle. And it was a lot. You needed 30 or 40 registers. So if you actually have some wires across the whole chip, you can need a lot of registers. And the fact that interconnect registers give you a huge number can now be useful. If you don't think you have to cross the chip that often, so you're going in and out of the logic blocks anyway, then the AMD solution is a pretty good solution. So I don't actually think there's a case where you can kind of go, that one's better. They each have their strengths and weaknesses. Does that make sense?
Can you combine them? Why doesn't Intel also?
Oh, Intel does actually do some of these delay chain tricks too. So the fact that I talk about this of AMD did some of the stuff more aggressively earlier and published it, but it doesn't mean, like Intel does actually have some delay chains as well. So and actually even before we had this, we did some of this delay, some of this clock skewing essentially by using stuff that was not in options we had in the routing algorithm that were never intended for clock skew scheduling. Like we found a few tricks where we could do it even though that had not been put in the hardware on purpose. But Xilinx has put it in the hardware on purpose first. Since then, Intel has also put some of it in. So this would be another one of those cases where you go like, okay, now both of them have something like this. Maybe it's a little different, but it's probably here to stay. Does that make sense? Okay, so Versal, which is Xilinx's latest FPGA, does something else clever on its clock. So this is showing what is this fraction of my clock period that is lost due to clock skew. Okay, so jitter on the clock, misalignment on the clock, etc. And especially for high frequency clocks, it's pretty significant, right? It can be 10% of the clock period for a lot of this. And obviously the trend is we want to push the clock period faster in future chips. So this is kind of concerning, right? If you're losing more and more of your clock period to it. Why is it getting worse? Basically process variation, right? Like you always design these clock networks that if you connect it all together in H-tree, in theory it has zero skew, but in practice it doesn't, right? Even with relatively thick wire and big buffers, there's some variation. So, and the percentage impact of that is largest on these fastest clocks, which are already the toughest to close timing on. So it's kind of where the exact opposite of where you'd prefer to have it. So Ultrascale built these variable delays at the last stage of the clock tree. So we actually have the ability to program in different delays on our clock tree at the very end. And what Xilinx did in Versal is thought, well, is there any way we can use this to reduce skew? Now, in theory, there is no skew, right? Like if you just use the targeted design, there's no skew. So the CAD system can't just say, well, program in a different delay to take out the skew because it's different on every chip, right? So it can't just statically program that in. So what Xilinx did is they basically added a little bit of extra hardware to their clock networks. They added phase detectors between adjacent clock networks, okay? So they know I'm at the very end of the clock network, and they know the leaf clock that's next to me, right? So they can build phase detectors that take signals from both of those and just basically check which of these is earlier, okay? It's relatively simple logic to say, this is earlier or that is earlier. When you configure in your design, they actually know what clocks you want. And the adjacent clock regions, like this last part of the clock tree, they basically turn on the phase detectors to see which piece of this clock is arriving sooner. I actually know this is supposed to be one clock, but it turns out the final leaf clock here is arriving 50 picoseconds faster than the final leaf clock here. And they essentially negotiate. They have a local negotiation where they basically change their delay chains to try to line up their clock edges. So it's a dynamic deskew technique on the chip when you power it up, okay? And it's specific to your design and your chip, right? Because that's necessary to take out the clock skew, because it has to be your chip, because it's taking out variation on the chip. Specific to your design, because it actually has to know what clocks are you trying to make, right? It's not trying to deskew everything from everything. It's trying to deskew your actual clocks. And they're in the Versal paper, so the one that you still have to this weekend to read, they say they can take out 60% of the clock skew doing this versus just having regular clock networks. Yeah?
Can you do this have power up or dynamically? Because if the temperature changes on your chip because it's heating up because you're doing
Yeah, that's a good question. I think that's why they get the 60%. They say they do it at configuration time, so I think it's a one-time thing. It's not, so Israel's right. You actually get these nasty effects like your chip heats up and the delays move. Now, if the delays of these two clock branches move in exactly the same way, you don't actually care, right? But if they move in slightly different ways, it means that you took all the skew out when you powered on, but the chip heats up to 85 degrees, some of it comes back. Based on their paper, it appears to be when you configure it, it can't take out temperature. And yeah, so that's my reading of it anyway. So, and I think that's why it takes out 60%. It's actually kind of an interesting idea. Could you take it out with temperature? To do that, you'd have to have the phase detectors running all the time. It's tricky. I guess clearly, like if you actually shift a clock for that cycle, you have to be kind of careful because you might actually induce a timing violation for that one cycle. and the end user of that chip's not going to be happy that, hey, almost all your timing transfers happened at a higher clock rate, but every trillionth one, if you heat the chip up, yeah, that one failed, because it's like, well, that is my system crashed, right? Like, and man, that's going to be a hard issue to debug, right? So, yeah.
What does this mean for CAD tools, though? For example, if I want to route my network at 600 megahertz, and I say, okay, so if the skew is 59%, it'll be bad. But if it's 60%, it's good. So how does a CAD tool know when too much skew is too much?
Yeah, so this will be part of their timing models. So the CAD tool is just going to basically run with either an assumption that it's zero skew or the skew that is essentially deterministic, right? Given they have all these delay chains, it's probably just assume zero skew, because they're like, well, the final stage is for us to zero out the skew and then make the skew whatever we want to be and all that kind of stuff. Your final timing sign-off uses delay variation numbers, brings in all the clock skew, etc. That final timing sign-off would be informed by characterization data that says you essentially have probably a lookup table. You can use this skew, which is less than what you'd get if you had uncorrected on-die variation. But I mean, the CAD tool would have been given that on-die variation in a lookup table anyway. Like that's the kind of thing you need characterization data to actually know to begin with. And they'll just, if they say we can count on 60%, they'll multiply by 0.4. And if they get nervous, they'll multiply by 0.5. Does that make sense? Okay, so that's it on clocking. So any questions on that? Okay, so I'm going to cover the second of the 4 topics that we're going to talk about today, bus-based routing, okay? It's probably not quite as long. Okay, so the idea behind bus-based routing is that most of the design is multi-bit quantities. Your finite state machines, control logic, they're often 1 bit, but you're doing floating point adds and so on, or 32-bit integer multiplies. I can identify buses of this whole operand is going here, not 3 bits here and 6 bits there. So, but FPGAs route every bit individually between LUTs. There's like, muxes that are controlled for every single routing wire, which means you fundamentally have per bit control. So maybe we could save some area if we routed entire buses, because we think design should be mostly buses. Yeah, what do you think?
Counterpoint. When you think about the actual routing muxes themselves, if you're programming 1 CRAN bit for every entry of the mux, because it's basically just a big bunch of like custom registers. So if you were to do, all this would be saying is, okay, we're just going to program all the bits together.
That's what it does do. You're right. So I think what Isidore is saying is like, well, he's already leaping ahead to, I don't think I'm going to save that much because all I can save is SRAM. Because what you're going to do is you're going to wind up with still needing all the muxing. You're just saying that these muxes have to be controlled in the same way. And you're actually exactly right, right? So that's actually one challenge with this, is you can't get rid of the muxes. All you can do is control them with the same SRAM cells.
Save that much.
So there's, see, this is a good intuition. There's a graduate student who probably wishes you had told him this years ago. And you're going to see what his name is in a couple minutes. Yeah.
Also makes the CAD tools easier.
It makes the CAD tools easier. Yeah, so CAD tools could be faster if you wrote this way. So it's a logical thing. Yeah, the savings are SRAM bits. So we fundamentally save SRAM bits by basically making them control like a whole bunch of signals together. The cost is we might waste wires and switches. If we do this and we made a whole bus of wires go in one direction, but it turns out they didn't all want to go that way, like we're going to waste some of that. So that could be our cost. Okay, so what does this look like? So this is Andy Yee, now a professor, so it worked out okay for him. But yeah, maybe you could have told him this years ago. They have a paper on this. What they did is they took 4 just regular logic blocks, and they basically said, okay, we're going to make 4-bit buses. They actually looked at different bus widths, but this picture is 4-bit buses. So what does that mean? So 4 outputs come out of here, and they share SRAM bits, so they choose to connect all 4 of those to 4 routing wires. And it's either all or nothing, right? Either all 4 are connecting to these 4 wires, or none of them are. Then they get to a switch block. All 4 of them can go left or not go left, right? But it's always a coupled decision. And then, for example, all 4 of them can go into these 4 inputs, or none of them can. So they're always sharing the SRAM bits on these. And then they keep some of the routing wires. They don't do this for all of them. They go with some control signals and so on. So we're going to have some other routing wires where there's still 1 bit. right? We don't share the SRAM cells. It actually works exactly, basically, as Isidore predicted. So you get gains, but they're relatively small. Why are they small? Well, they got about 10% area reduction on designs that had buses. Now, most designs have buses, so that's not a big limitation, right? They call them data path designs, but that's the dominant in pretty much any large design. Their best architecture had relatively narrow buses, 4-bit bus widths, and they made only half of the wires bus-based. The reason why is because there's all sorts of data widths, right? They could choose a 32-bit bus, and that would be more efficient when they had 32 bits. But when they had 8 or 16 or 3, it's going to be wildly inefficient, right? There's a really big cost to that. So they found better to use relatively narrow buses. If you need a 32-bit bus, well, you have to group 8 of these together. So we won't get quite as much savings, but it's not bad. They only made 50% of the wires bus-based. And basically, yeah, so there's all sorts of different bus widths. So they have to be careful about over-specializing. There's also irregularity in the data path. You might go, I'm working on 8-bit quantities, so it should fit on an 8-bit bus. But sometimes your 8th bit is special. You know, you've got overflow detection on it. Maybe your bottom bit is different. You know, you're sending in a carry in that's different. So even if your HDL kind of looks like 8-bit quantities, sometimes you see there's irregularities at like the top or the bottom or something. So what the CAD tool can actually route together is smaller than what you think in your HDL. And the final thing is just the gains you get is SRAM, which is about 30% of the area. So you know, you can save some when you use this successfully, but you waste a lot when you don't use it successfully. So you can get small gains, but not huge ones. Yeah?
Do they explore heterogeneous architectures where you have like a variety of different bus widths?
No. So they explored like these 2 choices. Bus, they tried different widths, and they tried a different fraction. But it's always 1 bit and some bus width. Okay, so yeah, so this idea probably isn't worth it in regular FPGAs. But there's a way you could try to build on this and maybe get bigger gains. So they did this in an otherwise conventional FPGA. We could change to something called a coarse-grained reconfigurable array. How many people have heard of CGRAs? Okay, so a few people. So they're a lot like FPGAs, but instead of lookup tables and which are like a single-bit functional unit being your key operation, they use larger functional units, like entire ALUs, and then they use bus-based routing. So they're kind of optimized for multi-bit data. And so they're changing 2 things. They're changing the logic block to not be based on LUTs. Now, FPGAs have DSP blocks and RAM blocks, which are also kind of fundamentally more coarse, but coarse-grained reconfigurable arrays basically just take the LUTs out. Like, everything's more coarse. That means, well, if there's irregularity in the data path, you just can't do it to some extent. So it fundamentally fits better in a bus-based architecture. You've got potentially bigger wins because you shrank your logic blocks as well. And the other thing you'll find in CGRAs is they tend to have much more limited routing flexibility. So an FPGA tends to have switch blocks with quite a lot of switches. You can connect the wires in many ways. Some of the muxes are relatively big. And part of that is you've got these SRAM cells that consume a fair amount of your area. So it kind of changes your cost function to you can tolerate a reasonable amount of muxing. You'd like to take some out, but it gets dangerous to take too much out, and you won't save enormous amounts. In a CGRA, basically to get big savings with this technique of doing everything by a bus, we want bigger savings than we can get in an FPGA. It's not enough to just take the SRAM out. You got to get a lot of the muxing out. Because if you've got too much muxing, then the fact that it's bus-based muxing doesn't help you much. Like if I mux an entire bus 32 bits at a time, that really means I need 32 muxes. If all those muxes are pretty big, I just don't save that much by the fact that they're all controlled by the same SRAM. So when you look at a CGRA, you'll usually see a lot of like local interconnect, a lot more restrictive interconnect. It makes their place and route problem more challenging. Like you'll wind up with a lot of solutions that just won't route. But you need to do it that way if you want to. It kind of makes sense to do it that way because if you put too much routing flexibility in this architecture, it's kind of unbalanced. You wind up with functional units that are more specialized, but so much muxing between them, you still don't get something that's very efficient. Yeah?
2 quick questions. First, this device seems a lot more restrictive. I could just do this on an FPGA and just make the functional units out of my FPGA functional units.
You can. So anything a CGRA can do, an FPGA can do. The whole goal, though, is maybe the CGRA can do it more efficiently. Right? So, because ultimately an FPGA can do anything. So if the argument is, can I do everything? You win. But then there's like, well, can you do it in this many watts or in this many dollars?
And then the second thing is, who makes these? Like, are there any commercially available CGRAs that are?
So I've got a couple that I'm going to show you. So the kind of CGRA is also a very loosely defined term. I've given you here effectively about the best definition there is, which still I could drive sort of a truck through. Like you can make a lot of things that fit in this definition. Samsung had one called Address that they used several years ago. Renesas has one. So some companies have had CGRAs and they've used them in some of their products. Usually they're internal products. They haven't sold them to other people that much. So I'd say that CGRAs have been kind of a niche. There's been a reasonable amount of research done on them, and they've been used in certain sort of proprietary company products. But yeah, Samsung and Renesas being two of the ones. But I could point at a couple that I would say have more market share and I think are good examples. Does that make sense? But like I said, CGRA is actually a very broad term. The ones that I'd say have been more niche have been, I guess, less flexible. I would say the ones that are less flexible have struggled to find a market where they work well. And you'll find lots of academic ones that fit into probably the less flexible. Does that make sense? Okay, so I'm going to just pick two architectures that I can fit in that bucket that I'm calling CGRA, even though they're quite different. Okay, that shows it's a pretty big bucket. So this is a paper called Plasticine. It's from ECE 2017. It's a nice paper, so go read it if you like. I didn't assign it. If people want me to assign it, you can post it on Piazza, and I'll make a questionnaire. You can get credit for it. But it is like 14 pages long, so it's going to make you work for it. Okay, so, and this one's also interesting because it was commercialized by a company called Samba Nova. Has anybody heard of Samba Nova? Samba Nova makes machine learning accelerators. They've raised somewhere between $600 million and $1 billion in capital. Okay, so they're like perhaps the best funded of the machine learning acceleration startups. So if you're just going by who raises the most capital, I think Samba Nova is currently leading. So anyways, that's interesting. This architecture has commercial heft behind it too. This is the academic chip though that created that startup. Okay, so what is this chip? So it's this interdigitated set of blocks. They have two kinds of blocks. They have this PCU, and I'm circling a whole bunch of them. You notice there's a pattern of PCUs. PCU means, I forget, I think it's like programmable compute unit. That does the compute. It's basically their logic block. Okay? What is it? It's a lot bigger than a logic block. It does 16-way SIMD. Okay, so it's working on vectors of size 16. And it does 32-bit operations on each. So it's intended not to do 1-bit operations, but 32-bit, and it's not intended to do them one at a time. It's doing them on 16-way vectors. So each of these PCUs is a lot, okay? Also, I kind of lied when I said 16, well, it is 16-way SIMD, but then within each PCU, they actually cascade 6 functional units in a row times 16 element vectors. So they have a lot of functional units inside one of these PCUs. It's pretty big, okay? Then they need the ability to access memory. Okay, so off on the edges, they can access, DDR, just like an FPGA. But their main memory is these PMUs. So let me erase these. Okay, so let's get rid of the PCUs. The other things here that are interleaved in the array are PMU. PMU is programmable memory unit. This is their BRAM. Okay, and it's actually not as different from a regular BRAM as maybe the PCU is from a logic block. It's 16 kilobit RAMs. So it's kind of like a big BRAM. It's like 16 BRAMs stuck together with control logic to do things like FIFOs. And the reason they have 16 of these is so you can send in like a 16-element vector. And if it goes to 16 different memories, they can all get serviced in one cycle. So that's the basic idea of what this PMU is. And then in between these things, they have these black wires, okay? And these S's. So the S's are switch blocks, and the black wires are routing. So this is interconnected with spatial routing. It's like island-style routing, but they're not routing individual bits. They're routing 32-bit buses. Well, they actually do have a few 1-bit wide signals. So they are routing some individual bits. They need that for control logic. So there are some 1-bit wide ones. But then most things are 32 bits. And they can route 32-bit quantities at a time. But the interconnect, more of it is actually routing really wide stuff. 32-bit quantities times 16 vectors, 16-element vectors. Now, they don't say exactly how wide these links are. So I think there's some serialization taking place. You know, if I take 32 times 16, that's like 512. Did they make these links 512 wide? I don't think they did. Okay, what I think they're doing is if you want to send a whole vector, it takes multiple cycles, and then it's gathered together in a FIFO in the PCU or the PMU. They don't go into that much detail about like precisely how many wires are there, but it's a lot, and it's optimized for transferring multi-bit data. Okay, so let's look inside the PCU. So the PCU, as I said, is these 32-bit functional units. So this is like their LUT. This is their logic block, and their LUT is a whole functional unit, can do 32-bit floating point. They don't build one of those functional units. They build, it's parameterized in their architecture, and what they find is best was 16-way vectors. That's what worked best on their set of applications they tested this on. So while this is showing essentially 4 of these things in parallel, really they did 16 in their final chip. And then they're showing that these things can be cascaded. So this is like your local interconnect inside of a logic block, but it's between these big functional units. This is showing 4 stages of cascade. What they actually found worked best for their architecture was 6 stages. So this is a pretty big logic block, right? 6 times 16, 32-bit functional units. If you look at this local interconnect, it's got a certain complicated pattern, right, that affects what is the muxing. This pattern was determined by them looking at their benchmarks. They basically made a bunch of benchmarks that do kind of classic compute algorithms, and they saw what are the communication patterns, and they made sure the local interconnect could handle those. So that's how they came up with that. Where does the data come in? Well, they've got basically inputs coming in from that routing that I showed you. Okay, it's coming in on the bus-based routing. It goes into FIFOs, and it goes back out. They also have these their control logic is essentially some programmable state machines. So it's difficult to say exactly what they are. You know, are these lookup tables? Are they something else? It sounds like they're state machines with some amount of low-level programmability, and they can take in 1-bit wide inputs and send 1-bit wide outputs to the routing. So there's some single-bit quantities too. So yeah, it's a mix. Does that make sense? Don't worry, it's like this is, I don't expect you to, it's a complicated paper. So like, you know, if you kind of go, I don't think I could reproduce the exact pattern, don't worry about it. Neither could I. You're kind of getting like, what is the general idea here rather than like every detail of the wires. Yeah. Yeah.
So is it possible to basically stop increasing the width to clock the basically routing faster than the functional units?
Probably. They don't actually say, they don't give that level of detail in the paper. I mean,
Now, is it possible to do that?
you could do it. And in fact, they might do that, right? So these switch blocks have registers in them, right? So this whole architecture also uses essentially registered routing. It's going into FIFOs. So they could definitely, they might be able to clock it faster. But I don't know the answer to that. I guess one other thing I should say is the actual array is bigger than this. So basically every diagram I'm showing you is like kind of scaled down because the full diagram is too complicated. I forget the precise dimensions, but the exact array is actually bigger than this. Samba Nova's latest chip, commercial one based on this, they say has 1,000 cores. I don't know what a core is, but it probably means PCU plus PMU. So you can guess it's maybe 30 by 30 or something in their latest chip. So it's a reasonable amount of spatial spread to have that much. So, yeah.
I know that CGRAs are often used in heterogeneous environments, so you have a CPU and a CGRA that communicate with each other. Is this often used as a coprocessor? Because I've noticed that they use 16-way SIMD with 32 bits each. That's 512. That's basically like what most processors do.
This is intended as a coprocessor. Like, I mean, this is intended as an accelerator. You're not going to run Linux on this, right? So there are commercial systems. They take these, they put them in big boxes that connect up to a bunch of Xeon servers feeding them data and so on. So there is more stuff, but this is targeted at like highly repetitive, something's got a lot of compute density, like deep learning, right? There's a good reason why there's so many accelerator companies chasing deep learning, because they have a highly repetitive computation and a very large amount of money to spend on it. So, okay, so that was the compute unit. I think I forgot to show the memory unit, but the memory unit is, similar idea. Okay, so you'll find that there's a bunch of block RAMs in it and these FIFOs and so Okay, so the results that they get, so they compared this to a Stratix 5 FPGA, which is the same process node, because this was done in 28 nanometers. They took 13 compute kernels. You can go read the paper if you want to see what they all are. And they compared on power performance. And they found that they got large power performance gains. They varied from 1.6 times to 77 times versus the FPGA. Now, there are, however, huge caveats on this, okay? So I think you can only take these results as, interesting. But, okay, why? It's again, well, I mean, I'm not it's a lot of work to build a system like this and then evaluate it, so I'm not critiquing that there's a perfect way to do this, but it's important when you read these comparisons, you don't just read the abstract. And the abstract says up to 77 times better. I remember being at this conference, and like Stratix 5 was one of the FPGAs I helped design. I was like, 77 times better. I'm going to read that paper carefully. So you got to read past the abstract. Okay, so the first thing is all of their applications they do in 32-bit floating point. So clearly that's not very beneficial to an FPGA. Stratix 5 was the last Altera FPGA before they put in hardened floating point. So this is not going to be a good fit to the FPGA. They also, okay, so their way of programming this is they have their own custom hardware generation flow, like a specific HDL that I've never heard of before, that they use to kind of program this. Because clearly this looks different. Right? And that's been one of the challenges with CGRAs, is if you make something that has a unique programming model, it's not quite clear what your tool flow is. So you have to kind of make it up. So they made up their own tool flow. And they used that same tool flow to generate the FPGA implementations. So it's unclear how good that is. It's their own HDL or one that they grabbed from somewhere and modified, and it spits out VHDL for the FPGA. But it's completely unclear how optimizes that compared to like a hand-designed one. Their biggest gain is on a CNN. That's the one that gives 77x. So, and this result looks a bit odd then, because you go, well, who does a CNN in 32-bit floating point? It's basically no one anymore. Now, maybe in 2017 you had some, to be fair. But nowadays you would never do that. And it makes no sense to do it in a chip that doesn't support 32-bit floating point. FPGAs do very well on CNNs if you use one of those data flow style accelerators that I told you about. But this is very unlikely to be building some kind of data flow accelerator. It's unclear what it's building exactly. So I think you have to take the result with a grain of salt. You can't really say how well it did versus this. Yeah.
Would it be more fair then to compare it to a newer FPGA architecture that has floating point than just scale for performance, like scale for process technology?
Well, what they would do then is probably take Samba Nova. Right? They'd take their more recent process technology against an FPGA. So FPGAs have evolved, they've evolved. That's probably the best comparison. But you also probably, Frank, you just can't really do CNNs in 32-bit floating point. Because no matter what the answer is, you just say that's not the way anybody does it. Right? It doesn't need 32-bit floating point. Now, some of their other applications do fit 32-bit floating point. Their matrix operations and so on, where you need at least 32-bit floating point. So it's perfectly reasonable. But it's just not reasonable for this one. And you always have to challenge. That's why I had people read that Intel paper versus GPUs. It's a very difficult thing, but you always have to ask, how good is your baseline? Did you optimize it well or not? And they don't say much about it. They just say we generate FPGA HDL from the same flow. It's just completely unclear. There's no comparison to what have people gotten. Essentially, it would be good to do a sanity check. If you're going to do a CNN, for example, there are a lot of results on that at this point. You should go compare to some of those results too. Because those are people targeting that device. What did they get? Does that make sense? And if it's close to what you got, then you could say, well, let's just use our flow. But if they're 50 times better, then you have to say, well, okay, this flow is not getting good results for the FPGA. And it wasn't designed to target FPGAs, so that would be okay, but you just have to know.
That makes sense. And the other thing as well is for CNN, do you think it would be fair then to say that they're going to do 32-bit on their architecture, but compare it to something like 16-bit or lower on the FPGA and say 30-bit?
I mean, it's difficult. You probably have to do both then. You say, well, what if we did 32-bit? What if we do 16, et cetera? You might have to give a more full set of results. Now, I would imagine that their Samba Nova architecture, where they commercialized it, can do more than just 32-bit floating point. So they would probably do new comparisons with it. But they've never published those. Well, they publish, numbers that say we're really, really good. But there's and it's probably true. But like a white paper is much more difficult to validate because never gives. It doesn't say we win. We win 2 out of 3 times versus our competition, or we win 40% of the time. Like you never see a white paper that says that, right? Like it's written by marketing. It always talks about the parts that are good. So, what's that?
Do they have any cost center? Someone actually
Well, so that's what's interesting. You kind of one of the challenges with CGRA is what is your programming model? Because what you just saw is so unique. And the paper's interesting. They talk about how we can program this, but it obviously is challenging. You're trying to teach people to describe their computation in a certain way and then a whole bespoke tool flow. So Samba Nova, if you go look at their material, their hardware, which is what they originally were formed to create, is this CGRA, or an evolution of it. But if you look at what they want to sell now, they want you to use their hardware, but they want you to use it by paying them to train machine learning models for you on their hardware. Okay, so I take that as a statement. It's probably not a bad idea. So they're like a full service ML company. Don't come to us for the hardware. You come to us for the models. We run our hardware to make it all work. But it probably means this is pretty hard to program. Because they basically go, don't ask us what the programming model is. The programming model is you put in money, models come out, right? And like, who could argue with that? So it's reasonable, but obviously if the programming model is that difficult, it's difficult to scale up to many, many applications. Works fine as long as you're writing them all yourself. And sometimes even that can be a problem. Like if it's difficult enough, it can be hard for you to scale internally enough people to keep up. But that's hard to say. So, whoops. Okay, so I'm going to plug this in. And I think we'll take, okay, so we're going to take a break and I'm going to do an emergency power up. Let's talk again at 5:51. I have lots of material, so we'll see if we get through a bit more before we run out of time. Hey.
I just have a question. So,
Sure.
when you talk about clocking closer to the power plane,
Yeah.
could there be like interference between them? So when there's
The power's very
from-
quiet. CGRA. And as I told you, the term's really loosely defined, so who can contradict me? Okay, so this is Versal. Okay, the Versal paper that I assigned has lots of interesting stuff, but it's primarily about the programmable logic. It doesn't talk about the AI engines. So, how many people know what an AI engine is in Versal? Okay, so most people don't, which is fine. Okay, that makes me feel good I put this up here. Okay, so Versal is Xilinx's latest FPGA family. So it has a whole bunch of PL, programmable logic, and it has IOs and high-speed transceivers. So regular IOs, and I told you that high-speed transceivers tend to, you can't have too much programmability, they don't run fast enough. It also has a hard processor. Okay, so this is their processing subsystem. It's, I think it's like 4 ARM cores and caches and so on. Okay, so you'd find all that stuff in Intel and other FPGAs too. But the thing you wouldn't find is what's on the top. And this is in about half the Versal devices, not in all of them, because some people don't need it. But what they built in Versal is what they call an AI engine array. AI does not stand for artificial intelligence. It stands for adaptive intelligent engines, I think. They actually originally put it in for 5G communication. So the truth is they actually decided to do this on something other than AI. It turns out communications, as I told you, has lots of signal processing. So this was architected for signal processing. But it turns out it's also, AI also has lots of things that look like signal processing. A whole bunch of matrix multiplications, a whole bunch of convolutions. Okay, so what is this AI array? And the reason they put it in half the chips is like, half their customers are like, I have no use for this. What I want is programmable logic. But other customers, they believe, can use this. So they've put in a form of CGRA. Okay, so what is the CGRA? So let's see. It is, the size varies. So from 8 to 400 vector processors. And so this is what their basic tile is. They have an AI engine. AI engine means vector processor. Okay. It has a little bit of local memory. It's not very much. It's like 32 kilobytes. And it's not a cache. It's like explicitly managed local memory. And then it has spatial interconnect. So bus-based interconnect to the things around it. So that's why I say it is a form of CGRA. It has 3 kinds of spatial interconnect. And let me show you that on this next one. Okay, so the most important one, the one that's most similar to plasticine and a conventional CGRA are these black ones. Okay, so the black ones are, they call them the stream interface. You connect to a 32-bit wide bus, and that 32-bit wide bus goes through switch blocks and can gradually go across the chip. It actually is, so we're going to talk, if we get to it at the end of the course, or end of this class, about packet switch NOCs, where they can actually change where you route based on a packet header. This can actually do packet switching as well, but their CAD tools don't currently support that. So they basically just use it as a switch block that is configured and always does the same thing. So just like a CGRA. Okay, so that's how I can communicate with anything across the chip. The red lines are essentially like the AI engine version of like Direct Connect. Basically, each of these vector processors has some dedicated memory where it keeps its data, it keeps its program. But it can also read from and write to the memory of the AI engine to its immediate left and immediate right. So it's like Direct Connect, right? I can go to its memory. And then the last thing is this green line, which they call the cascade interface. The cascade interface is basically like a hardwired interface. It just goes to the block to my left, and I do that all the way through a row, and then I go down one, and then I go to my block to my right. This is basically adding up accumulation results. It's very much like the way I showed you how the DSP blocks in modern FPGAs can chain their accumulation results with dedicated routing. That's what this cascade interface is. So they clearly, they're thinking about this for signal processing, so they really like the way DSP blocks can just chain their accumulators, and they just did it in this architecture, even though it's a vector processor. It has like a DSP block-like accumulation chain. Let's see, what can the vector processors do? They basically can do, their data path is 256 bits wide. So they can do 8-way 32-bit floating point, or they can do 64-way 8-bit operations, and they can do various things in between. And they even have a few tricks where in some cases for 8-bit they can do, even instead of 64-way, they can do 128. But the basic idea is a 256-bit wide data path that you can just chop up into various precisions. So they're optimized for high parallelism. Let's see, I already just talked about the stream interface. That's your bus-based routing with registers. I talked about the direct connect. Yes, I talked about all that. So they have like these 3 different ways to communicate. There aren't a huge amount of like direct comparisons of how efficient is this versus programmable logic. So if you want to, for your research survey paper, you could go find those, summarize them nicely. I'll share them with the class next year. So one that is interesting is this architecture has been used to do CNNs, performs well, it gets good numbers, but HPipe NX, like HPipe on Stratix 10NX outperforms it. So I have one data point where my group built a CNN accelerator which does significantly better, about 3 times better than the Versal AI engines on a CNN application, but where the implementation is very optimized, right? We built a data flow accelerator. So yeah, so that's one comparison I know well, but I'm sure it's also winning on other cases. So how do you program this? I would say it has a better developed programming model than plasticine, because the plasticine paper at the end of it, I could not describe to you the programming model, except it has many components, so I would not entirely know what do I send in to get a program. Now this is a commercial product, so also it tends to be more mature. But you send in 2 things. You send in kernel software, which is basically C++, where they've made special template for their vector instructions. And that's what's going to run on each AIE processor. So you can say run this on every single one, or run this on one and run this one on the one next to it. And then you write in some more C++ code that basically just calls built-in functions which essentially can create a graph, right? So you create what is the pattern with which these will communicate. I want this one to communicate using this cascade chain to the one next to it. I want this guy to communicate with this guy through the stream interface. Basically make API calls, and it essentially reconstructs a graph from your software. So, but it's all done in C++. It's a very stylized form of C++, but that's what you get. And the reason they can't use the packet switch capability is it's like a static graph. What their tools expose right now is like I always communicate with the thing one element to my left. Packet switching would be this packet, I'm going to send one to my left, this packet, I'm going to send one to my right. They don't have the ability to do that in their CAD tools right now. Yeah.
First, that's a CAD tool limitation, not a hardware limitation.
Yeah, they have said that the hardware can do packet switched, but it appears, clearly the programming flow is optimized for just always do the following.
Yeah, that makes sense. Second, in terms of what they're actually there's no place and route. Like you described, like you're basically deciding as a designer, I want this here.
No, they will place and route it, but the place and route is, so there is a place and route in it. The thing that they pointed out, which is interesting, is it's a place and route of 400 things, which is like really fast, right? So they kind of go, you know, the FPGA people in the FPGA community complain about place and route times, but if you take the million things you're placing and turn it into 400, your place and route algorithms get really fast. so there is still a place and route problem there. You have the ability to control, put this here or put this there, but you also have the ability to just say, just give me the stuff. And so much like an FPGA, right? Where you can control where things go, but more commonly you don't. With these tools aren't that new, but the tools are never as mature for anything that's more unique. So it's probably more from talking to them, it's like somewhat more beneficial if you give the tools hints than it would be with the FPGA tools, which are pretty good at dealing with like, just figure it out.
Yeah, because these are running programs, it's harder for you to say, like, deterministically analyze it and say that they...
You kind of have to say this is talking to this and so on, but you can say, you know, I'm talking to, I guess you could say I'm talking to this thing at this physical location, I'm just talking to this other kernel. Does that make sense? So you can leave some of it to the place and route engine, but I guess in a lot of their key use cases, you do know how things are laid out pretty well. Okay, so what's similar to plasticine? Well, it's targeting word-wide functional units. This is not targeted at like individual bit processing. It is targeted at vector processing. So the processors can also operate on scalars, but if you were only doing scalars, this is probably not the smartest architecture. And their routing is also, the most important routing is bus-based and registered. But interestingly, they have these things that are, you know, kind of like direct connect and DSP cascade chains that are kind of even more directly inspired by FPGA logic. What's different from plasticine? So, you know, plasticine, you configure the data path, like you program in, do exactly this, and that's what it does. And you control these like state machines to say what to do next, and they have a processor. So, you know, you have branches and whatever. That's how you control it. My guess is that's an easier programming model and a bit closer to standard. Like it's C++ with a bunch of extra templates. You need to be thinking about it, but probably easier to get your head around. So the cost of it is basically, what did it cost in the Versal AI engines to have an instruction stream, right? Versus Plasticine, where they said no instruction stream, right? You just configure it and it just does stuff. And I think it's actually an interesting question. I don't have an answer to that, but because these are operating on relatively wide vectors, the instruction stream cost has been amortized. So, this seems like a reasonable approach to say, let's try to make it a little bit more general programming model, make it a bit easier, and hopefully the cost is not too much. So yeah, I think that's an interesting thing for someone to quantify at some point, but I've never seen anybody quantify it. Any questions on that? So, okay, so that is it for CGRAs. We're on to the third topic. So don't worry, I won't go forever. We'll just it's on the web. Okay, so this is kind of interesting. It's something called more than Moore. It's not unique to FPGAs, but multi-chip integration is kind of an interesting topic these days. Let me see if I can make this go away. Let's see. Okay, so the idea of silicon, who knows what a silicon interposer is? All right, so I'm going to explain it, but this gives me an idea. Okay, so the idea of using silicon interposers is we're going to make a system that gets packaged up and looks as if it was one chip, but inside it really isn't one chip, but it behaves like one, okay? So Xilinx in the FPGA industry was the first company to do this. And what they did is they went, okay, here's like a conventional, what you call a monolithic FPGA. So it's one big piece of silicon, whoops, and it's got a bit of everything in it, right? So it's got some I/O, some RAM, it's all in columns. And they basically said, well, what if we made 3 separate chiplets, okay? So that together, if you abutted these, they'd have the functionality of this big chip. Now, why do they do that? Well, because it's easier to manufacture, okay? So whenever there's a defect in that chip on the left, I have to throw the whole thing away. On the right, when there's a defect, I have to just throw away one of those 3 things. So that can actually give me much better yield and lower my costs. There's a reason that Xilinx probably did this before Altera, which is Altera has redundancy, right? The fact that they can repair the chip on the left means it's not as big a win for them to chop it into multiple pieces. So Xilinx introduced this at the 28 nanometer generation, and they've done it at every generation since then, so it means they clearly think it's a good idea. And their largest, what's called a 2.5D FPGA. So it's multiple chiplets, and then they're going to combine. I'm going to show you they combine these chiplets using interposer technology so they behave as if they were one chip. So that's called 2.5D integration. And they could make something with 2 million logic elements. And at the time, from either them or any of their competitors, the largest chip that you could make monolithically on the left was about half that size. So they could make something bigger. That's one advantage. There are always people who will buy the biggest FPGA, even though it's super expensive, because they're doing prototyping, or they're emulating ASICs, or they're only going to sell a few. And they're just really cost insensitive, and you can just charge them anything you want, almost. Especially if your competition has no answer, right? You could say, well, you could pay this, or you could just go away, right? But I know you're coming back tomorrow, so why don't you just pay this and save us a bunch of time? So there's an advantage to, even though they'll be relatively low volume, having the really biggest FPGA is quite useful. Yeah, is there?
The cost of crossing that boundary, hierarchy, right, the placing route. I imagine that going across the boundary probably has significantly less routing and more delay.
Yeah, you're totally right. So the big challenge is how good can I make this? How much can I make this? These are all the reasons I want to do this, but how much can I make from an end user perspective this look like this? Because if, I could always make 3 smaller chips, package them up, put them on a circuit board, okay? And I say, there's your big chip. The problem is the amount of signal I/Os you have between chips is much, much less. And their delay is much higher and their power is much higher than what you have on chip. So it's not the same, right? So you need to do better than that, right? If it's really just 3 chips, then you don't, we always had that option, right? You could always sell people more chips, but it doesn't work the same as one big one. Okay, so you can get better yield. That lets you make a bigger chip. You can save mask costs. So I showed you mask costs are multiple millions of dollars, $5 million in the latest process technologies. if I make this chip, like I make one mask and I make 3 copies, I get a certain chip. I make 4 copies, I get a bigger chip. So they do save a few masks. They can actually step out a few of their biggest devices. They do actually make chips where they have 3 of these. They make chips where they have 4 of these. And they don't have to make a separate mask. So they save a bit. But yeah, it has to be better than combining multiple chips on a board. And Xilinx, as I said, clearly likes it because they've been using it for several generations. How does it work? This is a picture from Xilinx. So they call the FPGA chips super logic regions, SLRs. So these yellow things are actual FPGA chips. For high-end chips, you use solder bumps, okay? And you flip the chip upside down to connect to the package. Okay, so that's the conventional. For low-end chips, you can use little wires coming out from the end, but for higher-end chips, you can't get enough I/O and you can't get good enough power. So all high-end FPGAs use solder bumps and flip chip. Normally, you would take one of these yellow things and you directly flip it upside down on the package. The package is this green thing. Okay, so packages are typically made with organic materials, and their metal traces are pretty big. Like you can't make really thin, like the wires that I say are thick and big, high in the metal stack on a silicon chip are ridiculously tiny to the wires you can make on a circuit board, just because of the differences in manufacturing technology. So your package is basically like a fancy circuit board, and it takes these signals here and puts them down to bigger solder bumps that go onto your real circuit board, okay? So what they've done here is they put something in between. They put this gray thing in between, which is a silicon interposer. And this particular device is 28 nanometer FPGAs, and this silicon interposer is made on an older process, 65 nanometers, because it's cheaper, and it only has wires, doesn't have any transistors. So the reason they do a silicon interposer is they can make a 65 nanometer silicon manufacturing process can still make much, much smaller wires than you can in a package, because a package is like a fancy circuit board. So they can get way more wires on this. And they can use much smaller solder bumps. So now the last thing they have to do is they do need to get some, so this basically allows them to connect a bunch of signals from one of these yellow FPGA dice to another one, right? Using the wires in the silicon interposer and these micro solder bumps, like really little small solder bumps. On the order of like 50 micron pitches, which is much tighter than the solder bumps you can get down here. You do need to get some signals out to the package, right? Like to the circuit board. And notice that your actual metal stack is buried, right? Like the metal of this FPGA chip has been flipped upside down and it's now in a silicon sandwich. So to get any signals or power and ground into this, you have to have something called through silicon vias. Through silicon vias are basically holes that are etched all the way through the silicon so that you get some connectivity into the package. Okay, and those holes have to be, those vias have to be relatively large. They're much bigger than the vias you'd have between regular metal. Yeah.
You mentioned something earlier about the package substrate being saying that it's organic. I know it's kind of a silly question, but do you mean like it's literally made
Like
of
plastic.
Oh.
When I say organic, it means like plastic, like organic chemistry. Does that make sense?
Yeah, I was just
I think there are some high-end ones that use ceramics. They're more expensive. They get somewhat better signal integrity, but they're less common. And it's still nowhere near as good as silicon. Yeah, when I say organic, I don't mean that they didn't grow it. You have a farm where you're growing your package. So, this is like just kind of a detail zooming in on that. So here's my FPGA die, and it has these micro bumps, and these micro bumps are 40 microns apart, which is pretty tight, and they connect to basically landing pads on the silicon interposer, which connects them, using wiring that you can't really see. It's too small. And then we get a few, well, what looks like a few of these through silicon vias. And the through silicon vias are also, on the order, from this picture, the through silicon vias are on the order of 20 microns or so, which is pretty small compared to a circuit board, but pretty big compared to like transistors. And the through silicon vias go all the way through the silicon. That's why they have to be pretty big, because they're like tall, right? And then they connect into these solder bumps that connect to the package. You can actually see the package metal traces because they're pretty big, right? So there's package metal traces that are on the order of 0.1 millimeters or so, which sounds pretty tight, but it's huge by a chip scale. And then we have some vias here that go down and out to solder bumps in the circuit board. So that's what this looks like. This is a TSMC manufacturing technology called chip on wafer, I think on substrate. Okay, so why they do this? So the number one reason is for yield. So let's figure out what they saved. So a simple but reasonably accurate yield model is called the Poisson yield model. And it basically says the yield, like the fraction of chips that I'm going to get working, is a negative exponential of its area times the defect density. So this just comes out of saying, I got a chip's broken. If I have no ability to repair, which most chips don't have, a chip is broken if a defect happens anywhere on it. So you go, what's the probability there's no defect? Well, it drops exponentially with how big my chip is and what the defects per centimeter squared is, right? So it's pretty intuitive. Okay, so let's say that I've got a chip that's 6 centimeters squared. That's a big FPGA. Okay, this is one of those ones you're going to sell for a lot of money to people who need a big FPGA. And let's say my defect density is 1 per centimeter squared. You will never get a foundry to tell you these numbers, but this is a number that you would get early in a process technology. Okay, and FPGAs go to do process technologies pretty early, especially the high-end ones. You go to the high-end process technology, you get the biggest FPGA. So, and the process gets better over time. So this would drop, for some of the processes we use at Altera, we'd actually see over a course of a couple years that this would drop by a factor of 10 as the foundry got better at optimizing it. But we do care about what it is early on because we want to sell these big chips before anybody else can, and you get design wins. You get designed into systems, and you stay in that system for maybe 10 years. But you got to be able to supply it now, not say in 2 years I have a fairly good feeling I could supply it, because that's a very scary thing for somebody making a system. Okay, so if I crunch these numbers, I get a yield of like 1 in 400 chips will work. Okay, so this is very close to 0. The number of die per wafer, I take the area of the wafer, a 12-inch wafer, I divide by my area of a chip, and then I multiply by my probability of working, and I actually get 0.3 chips per wafer, which means I actually run 3 wafers and I get 1 working chip. So you're going to have to sell this chip for a really large amount of money. You also have a problem if you just can't guarantee supply. Like somebody says, okay, yeah, that sounds good. I'm going to start my low volume manufacturing. I need 100 of them. And you go, like, I don't know if I could make you 100, right? Especially because this isn't fully random. Like there can be correlations. This week, maybe this month, maybe you get 0. So this is like basically bordering on unmanufacturable at this defect density. Okay, so let's say that I have the same defect density, but I now make 4 chips, each of them 1/4 of the size. If I crunch through the same number, I actually am going to get, it's huge. I get 66 working chips per wafer. Now each of those is only 1/4 of my systems. I need to put 4 of them together, but I still get 16.5 working systems per wafer. So I got a 55 times improvement in yield. Now you could say, well, you had to put those on an interposer. What if some of them didn't work? That yield is quite high. So it's true, it's not 100%, but it's pretty good. It's relatively close to 100%. So you get a huge win. As I said earlier, it's less for Intel because they have another technique of repairing their chips. But this actually gives you some idea for these big chips how important a redundancy strategy can be. Okay, now let's run this again though. Let's take like a mid-range FPGA, like a high-end family, like Versal or Agilex, but you take the middle chip, not the biggest, not the smallest. It's usually about 2 square centimeters. And let's say the process now is more mature. Okay, so it's a couple years later, it's been optimized, 1/10 the defect density. Your yield now is 82% of die. So you get 299 of the big dice per wafer. If you make them from the little dice, your yield goes all the way up to 95%, and you get 347 systems per wafer. So there's a gain, but it's not much. And the interposer is not free, and the extra packaging cost is not free. So probably for this one, it's debatable whether it's worth doing. So there is a trade-off here, right? Mature processes, smaller chips, this doesn't make any sense. Early process, big chips can be a big win. So the first chip Xilinx did this in is this 28 nanometer chip. And basically they have 280 vertical routing channels, and each of them has 210 wires. That's the channel width. When you hit the interposers, basically these lines where you can see all these like white things are where the boundaries are, where you have to go out to the interposer and come back in. and only 23% of the vertical wiring crosses. So why? Because that's how many of these micro solder bumps they can fit within a few millimeters of the edge. And they basically put solder bumps everywhere around the edge that they can to try to get as much as they can. So it is a big interruption in your routing fabric, only about 23% of the capacity, and it has more delay. In this chip, it had about a 1 nanosecond delay, which is about 5 times what their normal kind of workhorse routing wire had. So you're going to take a delay hit, and you're going to have to watch how many signals are crossing. Yeah?
If you fit more by basically saying, okay, I'm going to end my chip a little bit earlier, but still have those same number of wires coming into the end region, and then basically just spreading out the bumps vertically.
They do that already. So these bumps are spread out over many horizontal channels, and then they have a whole bunch of they've changed it from generation to generation. And the latest generation is basically every logic block that's within, I don't know, maybe 20 or 30 units, like the last 20 or 30 rows when you approach this, every logic block has a couple of signals that can make it across. So they have spread out the interface in order to basically cover this with solder bumps. I think they're limited by, if you get too far away, the interposer wires get too big. There are no transistors on the interposer, so you can't repower the wire. So you're up high in the metal stack at 65 nanometers, so it's a pretty thick wire. You can go a reasonable distance, but you can't go all the way from bottom to top. The resistance will kill you, and you can't fix it. There are no transistors. Well, to put a buffer, you got to come back up. All right? You got to. You can't. Well, you could, but that's another process. So the interposer that Xilinx is using is called a passive interposer. The metal stack is fabricated. There are no transistors. So they cannot build. There are new process technologies coming online where they can do transistors as well, but this one can't. So anyway, so the question is this okay? Xilinx did, I think, a very nice job of rolling this out. So their CAD tools basically hid it from users, which is a good thing, right? So you would just synthesize, place and route your design as usual. You didn't have to partition it. Partition is, chop it up, and that's what you'd have to do if it was separate chips. You didn't have to do that. If you have a really big emulation system, like you can emulate an ASIC, what they usually have to do is time domain multiplex the IOs. So there's no way they can chop it up across like 100 chips, or they have to basically send, time domain multiplex like 100 times the IOs. So it runs very slowly. It's intrusive. Designers are aware of it. Didn't have to do any of that, right? They just push the button and it'll work. So they modified their placement engine to understand you should try not to cross this. The question is, how well does this work? Basically, if this works well, then nobody needs to care. If it doesn't work all that well, then everybody's going to figure it out. So my group did a study of this, and basically in VPR, we put in a bunch of enhancements to understand these kind of boundaries, and to check, well, where do we find this kind of falls off a cliff? And this chart shows the result. Basically, we could cut around 80% of the wires in these vertical routing channels at these interposer boundaries, and it didn't affect our minimum channel width much. We didn't have to add much routing to the rest of the chip. If we went further than that, it started becoming the limiting factor. It's not working well, right? We're having to add routing all over the place. Xilinx cut in 28 nanometers 77%, so they're around here. So according to this result, they're in kind of the reasonable range. Their CAD tools, they've probably tuned more, so they can probably push a little further. Well, they might be able to push a little further this way too. So makes sense, works pretty well. It gets harder every generation because the solder bumps that they're using don't scale as well as the transistors. So they kind of get a smaller fraction every generation. So this CAD challenge will get harder and harder. So maybe go work at AMD. They need to hire smart people because you have to fight exponential growth. So the other thing that we found that architecturally made a lot of sense is these are like the most expensive wires you're going to get. They're a choke point. So this is a case where you don't use direct drive. You make them bidirectional with tri-state buffers. You make really big muxes in front of them. You're doing everything you can to make sure you're not going to waste any of these. One of the cases where you don't care as much about switches, you're optimizing for the wire count. Now, there are various academic papers where people are mapping things to Versal, where they say they can get, they do lose performance when they cross these boundaries. They did have to floor plan. So I think Xilinx has done a good job of their tools work, but at least in the recent generations, where this problem has probably gotten harder, people can tell, right? Like they sometimes have to guide the tool. But clearly, Xilinx still likes it. They keep doing it. Yeah.
I would assume that it's a good idea to put a register before and after this.
Yeah, you should definitely put a register before and after. And yes, that's also good design practice. It's deeply pipelined. It's good. OK, so Intel doesn't do what I just showed, where they take a big chip and chop it into multiple pieces. Well, not that way, where they make like a bunch of identical chips. They do use interposers, though, in a different way. They basically, this is Stratix 10. They make one big piece of silicon for the FPGA, and then they make separate pieces of silicon for the high-speed I/Os. And they put little interposers, that's what these green things are, is like little pieces of interposer silicon to connect those up. So this is heterogeneous integration. They're not trying to make one bigger chip. They're saying, hey, we'd like to tune the process differently for some of the high-speed analog we need here, so let's do that in a different process. And we can make sort of a replicable unit here, and then hook it up to a really big FPGA. And this is just a picture of what those look like. So Xilinx basically has one big interposer here, and Intel puts a bunch of little interposers. So otherwise, the technologies are similar. Let's see. The Intel technique has an advantage that they don't need through silicon vias. They can basically still get the I/Os from the FPGA die or these little chiplets. They can connect directly to the package because the interposer is not covering the whole face of the chip. So you don't have to drill through it to get at it. That could give them better signal integrity for the high-speed transceivers. Like when you start running at like 30 gigahertz, you kind of notice every little bit of capacitance and inductance. And in the future, there are basically active research by both Intel and TSMC on interposers that include transistors. And they're like not FPGA projects that use that yet, but there are processors that use it. So nobody's quite sure what to do with that, but there appear to be big rewards if you figure it out first. Because in the processor space, AMD did some clever things with chiplets before Intel, and it actually gained them a bunch of market share in the server market. So it's kind of, I don't know, it's interesting. It's kind of the Wild West. Nobody's 100% sure what to build, but at the same time, you can see if you figure it out first, you can actually gain a lot of market share. So, yeah.
Really stupid question, but I am really curious. Why not just take one FPGA die, take another FPGA die, and kind of do this really crosshatch pattern of up and down, and on the edges just have the IOs?
You could do that with this Foveros technology. So like you need to be able to join two active devices. And you need to check, well, what is the density of interconnect you can have to decide like what exactly are you trying to connect. If you're trying to connect entire routing channels, it has to be high density interconnect. So, but with Foveros, what you're just describing is at least a first order manufacturable. Okay, so that's it for interposers. In the last 4 minutes, I have like one last topic. But I'm going to go for it. So we'll see how far we get. Okay, so the latest FPGAs from, well, Versal did this first. That's why it's a really interesting paper to read as well. And since then, FPGAs from Acronix and maybe a half step from Intel have incorporated something called the network on chip. Okay, so here's the challenge they're trying to solve. You have big systems. They have high bandwidth hard blocks like memory controllers and PCI Express, talking to big modules like lots of with wide data paths. So you got a lot of data transit happening. And the traditional way you handle this in an FPGA design is you build a wide soft bus, right? So you can build anything, you just build it wide enough, 512 bits. And maybe you need these memory controllers need to go out to all sorts of stuff. So these wires can go a long way, and they might be very wide bus to move the bandwidth. Okay, so what does this mean? It can be difficult to close timing. You need a lot of pipelining. You chew up a lot of resources. There's muxing in here. If it's a 512-bit bus, if you put a few pipeline stages and some muxing in, it chews up a lot of area right away. And this is done differently for every design. Everybody connects in different ways. So it's like another thing you have to do in your design. You can't just get it from somebody else. Okay, so it means the system level integration is kind of costly and time consuming. Okay, so one idea you could have is, okay, something is used in most designs, it's expensive, it's a pain, maybe you can harden it, right? It's what we did for DSP blocks, what you do for block RAMs. And there's actually a proposal to do, so what do you think of this? Do you like this idea, harden the bus? Yeah.
This sounds very similar to the paper you proposed earlier where you make some percentage of them bus-based routing.
Yeah, but here I want to actually just harden the whole thing. Like I just bust from here to there. I don't want to just make bus-based routing because that only saved me a little bit. Like I want to get rid of the muxing everything. I just want to build, I don't want any configurability. I just want to build a bus. So,
How do you know where the modules that are receiving that bus are?
so that's your problem. Bus to where? This was a serious proposal with this Altera. I remember having a conversation with the VP of IC design. He was a great guy, but he's like, okay, so we get this proposal, like we put this bus from DDR because we have all these problems with time enclosure and it's getting wider and wider, so we have a bus to the middle of the chip. I go, what? Goes to the middle of the chip, then where does it go? I don't know, the proposals go to the middle of the chip. It's like, well, why is the middle of the chip better than the edge of the chip? Like, so that's your problem. If you harden this bus, like, so basically it is in most designs, it is costly, so that passes our first two checks for hardening. But our problem is we don't know what to harden so that it's usable. So I could harden all these buses, like build arbiters and wires here, arbiters and muxing there. It's great for this design. But basically then I change my design to something else with different modules, and I just have buses to nowhere, right? Like, so this is like the TTC, right? Like this is the way we planned this. This is how we got the Shepherd subway. So, yeah.
What if you make this kind of like when we were talking about the H tree before, you basically just have like maybe it goes down the middle of the chip into the sides, and then basically like there's maybe a few rows and columns where they're not everywhere like the bus-based routing, but it's just like every 30 blocks or something there's a big bus.
Yeah, so that's the right idea, right? So we can't do this, but maybe we can add in some more flexibility, right? This is just not reusable. So what we want is a more general system level interconnect. It has to be able to move data between arbitrary points, has to handle high bandwidth, in particular what's coming in from the IOs, and has to be pretty efficient. Okay, so what that leads you to is a network on chip, like a packet switch network on chip. So a packet switch network on chip, we can basically pre-build routers, and we can build links, okay? Which are just connections between routers that are bus-based. And if a module, like module 4 wants to send data, it basically sticks a packet header on it, like a little bit of data saying, where do I want to go? It then has, as it connects into a router. So the router has a port that the programmable logic can connect to. The packet will be divided into flits. So that's how much can be can transit one of these links at a time. So the link's 128 bits wide, a flit can send 128 bits of data. So basically the router sends the flits one after another, and all the routers are registered, and they examine the packet header to decide where to go. So they have muxes in them that are controlled by the packet header. So basically, I now can send data from this, let me show that again, because it's such a cool animation. So it can go from module 1 to module 3. And then module 3 reassembles the data. But basically, if I put a new design in, where my modules have all moved around, I can still use this, right? Because I just changed my packet header, and I can send it to a different place. Okay, so this module 5 is now sending stuff to PCIe, and it works. Yeah?
So this is no longer something that's invisible from the programmer. They have to explicitly...
You have to know about this. You can't just take arbitrary HDL and stick this in. You're right. And the reason you can't stick it in is because there's latency. These are registered, and in fact, there's also arbitration. Maybe somebody else is trying to send data through here too, and you have to be buffered for a little while. So it's natural to do this at the IOs first because, for example, your memory controller, there's all sorts of reasons why you don't know exactly when your data is going to come back from memory, right? Depends if you get a row hit or like a page hit or a page miss, whether it's a refresh cycle, all sorts of stuff. So you already had to design your logic that there's some signal that comes back that says valid. You need that signaling to go over the NOC too, because if you just assume it comes out 6 cycles later, your design will never work, right? Sometimes it comes out 6 cycles later, sometimes 10, sometimes 23. Yeah.
So in your Verilog, if you want to use this would be some like IP core that's provided, and you would have an interface where you're basically saying, I'm expecting something, and I'm going to receive like a packet. I'm going to receive a valid bit. I'm going to receive some data.
Yeah. So you can abstract that. So you're right. So okay, so I'm going to get there in a second. Okay, so this passes our test if it moves data between arbitrary endpoints. So we've hardened something, but we've hardened is more flexible. So it works. So how do we build this? We basically have a regular router. This is a well-studied thing. It's used in multiprocessors, et cetera, and we have links. Okay? If we add in for an FPGA, we need to add in this fabric interface. What is this? Basically, we don't know what we're hooking up to, right? That's unique. networks on chip and a multiprocessor, you know you're designing a core and a memory controller and you hook them up. In the FPGA, we have to make this more flexible because we don't know what's connecting to it. We also, what my group proposed some of this some years ago, and it's largely what's been done now in commercial FPGAs. So don't have any hard boundaries. That means that you can use the NOC, but you don't have to use it. Like you still have all your regular programmable routing. You can choose your compute modules to be any size. And this fabric interface gives you flexibility. It basically has time domain multiplexing, clock domain crossing. So basically the NOC can run at some fixed high frequency, and your compute modules can run at any frequency they want, can be much lower, and they can use a wider data word that's just slower. Okay, so I don't think I want to talk about all of this. That's the basic idea. Let's see. But yeah, if you go inside a router, there's a crossbar, buffers, and some logic to say which of the many packets coming in from different directions crosses right now. And I'm not going to, basically, I guess I'll tell you just a couple of, we did studies, which you can look at the slides if you want. Could you do this soft? And the answer is basically no, right? It's too inefficient. If you want to use these kind of packet switch fabrics, it's much more efficient to harden them. And there are different ways to harden them. You can look offline if you want. This is the one that's most beneficial in what commercial chips have done. Harden both the links and the routers. Compared to building it all soft, it's a lot smaller, like 27 times smaller. So you wouldn't really do all of this soft. If you're going to do it soft, you're better off to stick with the usual programmable buses. Let's see. So the fabric interface is pretty important. So basically, you want time domain multiplexing so the router can run fast with narrower flits. You can have wider things in the FPGA. You want this clock frequency to be anything, so you want to have basically a FIFO that has two different clocks. So you're not tied in any way. What's presented to the application designer is essentially a FIFO where you put data in one spot and it comes out somewhere else. So it looks like a FIFO. You can wrap an ECE interface, which is a standard around that. So now it looks even more standard. It looks like a FIFO that communicates with the ECE protocol. And that's what is now the typical thing that is done with the commercial designs. So you can't take arbitrary HDL and just stick that in behind people's back, but they have a kind of well-defined interface. And if you use system integration tools, which most of the major vendors have, where you can plug down IP and say hook it together, they can hook it together automatically. Okay, they can hook it together with soft buses, but they can also hook it together with a NOC. Yeah.
So the interface on that software that I would have could be like I have 128. I don't have to think with the flits or anything else. I can have a 1024 wide.
Yeah, like a common thing would be like the flits are 128 bits wide and your interface is 256 or 512, right? So they're going to typically be relatively wide because these NOCs are targeted at system level communication, meaning they're to move quite a bit of data. So a logical thing to tie them to is how much data can come out of a single DDR channel. Because if I can take that data and put it in in just one stream of data going over NOC links in a router, that's really nice, right? Like I can get at my memory from anywhere. So you'll find that's what we actually found when we researched this was a logical thing, and that's exactly what Xilinx chose to do too. Tie it to what a memory controller can produce, make sure your NOC bandwidth is that high, and then your fabric port bridges that to any module that wants to talk to it but can't run at the same frequency. The NOC runs at a gigahertz or more, so you're going to want to widen the data word by a factor of 2 anyway, maybe 4, depending on how skilled you believe your user base is. Right? So let's see. So I'm going to skip all that. I think I just told you this. You kind of go, well, how should I set the flits? A logical thing is find some of the endpoints you know. And it turns out if you look at DDR and PCIe, they have similar bandwidths. So we make your NOC able to handle that bandwidth over one link. It is now much easier for people to use this. So I'm not going to talk about that. It's relatively small. So the studies we did, we found that we could add a reasonable NOC that could have 16 routers. So there's a reasonable density of routers you can get to. And each link could handle the full traffic from a DDR channel, and that was only about 2% of the die size. And that's small enough that you can kind of go, well, okay, if it's usable by quite a few people, I can put it in. At like 10 or 20%, usually a vendor won't do this. But at 2%, if it's got some reasonable utility and maybe some future people will learn to use it over time, you can get it in. And it did go into Versal, right? So it was after this that they did it. And they said, actually, so I know the lead architect at Xilinx, or AMD, and he said that our predictions were actually good, right? So we published a bunch of papers on this. We presented them at AMD and Intel, except we underestimated how hard it was to fit all the wires. He said fitting the wires was way harder than you guys said it would be. But they did it, so it's good. So, okay, so I kind of already talked about this. So you need to use this where you have variable latency. And by the IOs makes the most sense. Yeah. Yeah, getting all the wires in the metal stack. We analyzed it. We said it'll fit fine. They said they fit it, but it was a royal pain. So it's probably they didn't tell me what area it took. I think it's right for transistors, but they said fitting the metal was harder than we thought. They didn't give me like a layout plot or anything. They just gave some gentle abuse. So, but it was fair. It was all in good spirits.
A typical design, you're going to separate up your modules by axis anyways. So this would be good for communicating between different modules so that you can place them in a
Yeah. So you can, yes. So you can use it to communicate with different modules. Where it's getting used the most is to talk to IOs. Like that's the key obvious use case. Trevor Bauer, Xilinx's lead architect, basically, gave a talk at FPL this summer, and he said, yeah, they use it. That's actually the only way in Versal you get at the memory controllers. So like, there's no option. You want to talk to memory, you're using the NOC. Okay, they didn't even build interfaces with programmable logic, so it clearly is working fine for that. Or they would have heard about it by now. So you can obviously also use it to communicate with all sorts of other things. And in his talk, he talked about, if I've got somebody complaining about congestion, et cetera, and I say, well, there's this great thing you can use to remove lots of congestion. And he gave examples of like they move communication between modules that are in the soft fabric onto the NOC and things get way better. But because the tools can't do it automatically, they have to sort of reach that customer and train them. So he was asking the community, can you find a way to make my life easier by just doing, which is a good challenge. If you can find a way to do that, that's good. That is the challenge of changing your programming model. This changes your programming model some. So they've been able to just insert it to the memory controllers. Like it's the only way to talk to our IP, so you're doing it for sure. But they got to kind of train people to do it between modules. Let's see. Okay, so I don't want to talk about this too much. You can read this offline. It basically says this is efficient. And I think it's also really good for the data center. The data center, we talked about how like Microsoft locks down the shell, pre-places and routes it. That kind of splits your compile. You actually have to compile all your I/O stuff, lock it down, and then stick everything else in the middle. A NOC is nice, where it can now distribute data from the shell throughout your whole device. So it makes a shell more powerful, easier. But I'm not going to go through all those slides. You can look at them offline if you want. There's some nice animations. I'm not going to go talk about that. But basically, it looks pretty good for also being nice for this data center style. Yeah?
And also for partial reprogrammability, if you want to have different pieces where you're swapping in and out, it's not like the shell will allow you to do that.
Yeah, that's basically the reason that the shell and role, what Microsoft calls, is an example of partial reconfig. I think there's a bunch of things that could be done for partial reconfig because the NOC makes things easier. If you only talk to a NOC router, you can now talk to anything. That's an easier way to do partial reconfig than we've had before, where if I talk to this module, I got to line up with its exact physical interface. So interesting research topic. I guess this is another thing that it does scale well with interposers, right? So I told you that as we keep shrinking the silicon die, we're getting a more challenging problem to cross interposers. Well, AMD has that. The NOC fundamentally runs at a high frequency. You can talk to a router from the programmable fabric. It time domain multiplexes your data together, so it's really high frequency and sends it over the links. That makes better use of your limited wiring that goes between different slices. And this is something that Xilinx is leveraging. And this is my last slide, I think. So basically, this is the Versal NOC. So the NOCs that most common NOC you'll hear about in academia, including what my group looked at, were meshes, right? They're nice and regular. They lay out well. And the Versal NOC does this look like a mesh? Right, so this is not, okay, this is poor artist rendering of mesh. So it doesn't look like a mesh, right? They have NOCs at the circles. They have links in the wires. But it is like a squished mesh. Basically, they lay out their FPGAs in columns. They want all the columns to be the same so they can just replicate them and kind of stack things. Essentially what they did is they took all of the vertical links in the NOC and squished them together in a limited number of columns. And then they made all the horizontal ones at the bottom and top. So it's not a mesh, but it's basically something that's sort of a squished mesh that lays out more easily in an FPGA style. As I said, it's the only way you can get at the memory controllers. They have about 100 fabric ports, like access points to these routers, so you can get at it from a lot of different places. And it provides pretty high bandwidth, a gigahertz at 128 bits wide, which is enough that they can take the full traffic from one of these memory controllers and just send it through one path in the NOC to anywhere they want. And obviously you can have a lot of those paths going on at the same time. So, and that is it. Sorry for going over time. So thanks everybody. I won't keep you any longer. Good luck with the last assignment in the research survey. So. Thanks. And sorry for going over time. I should have said if you feel like you needed to leave or felt like leaving, you could always leave, right?